What's up? I am Luna Halcyon, and I'm going to make this video about these topics. I'm going to do it all in one video, and I'm not going to stop. I'm not going to waste your time. If I can avoid it, I'm going to waste your time, because I don't know what's interesting about this stuff to you. I might put these in separate videos, just because they kind of do go together, but they also kind of go, they kind of go separate, but they do also kind of go together. So I might just keep talking, but I'm going to keep going back. I'm going to keep referencing this. So the first thing, counting in space-time, shape, geometry, shape, angle, dimension, functions, logic, and computation. These are all really closely related. So this is like the fundamental thing that you're kind of dealing with all the time. There's this thing called extension. Not everything is extension, let's say. Not everything is extension. For example, what's the difference between black and white? What is the difference between something and nothing? Why is there something and not nothing? And if there was nothing, would there still be a space that nothing is in? And there's nothing in the space. I don't know. Plus, there's thought. There's like, time is not just time. Time is the process of things changing, but the processes themselves are not time. You know, I am not time or space. I am not space-time. I'm not even a space-time, because I'm made of things that are more than just space-time, I think. Maybe I'm wrong though, maybe it's all extension. But that's like deterministic stuff, and that's like, let's actually do it like this. So this is space. Determinism is like kind of just nonsense, but in certain cases it's accurate enough to say that something is completely determined by past truths. But time, we're all pretty familiar with time. So time is like this difference between the past and the future. So there's the past, and there's the future, and then in between, there's the present. And we're in the present all the time. You're always in the present. It's your present. You're always in the present. Everything is always in the present. That's just the way time works. The past is anything that passed by the present. So really, it's like we're moving into the future, but all the possible futures are kind of like moving backwards and becoming the past. They're becoming more solid or something like that. But it's like, but we've also got solidity that we're like the possibility, we're still moving into those possibilities. So it's kind of like a weird, like, I don't know how to explain it, you know? It's just it's just shapes changing. That's the thing. Space is kind of an interesting way to understand that. So, what do I want to explain? Like, this is a space. A line is a space. You can put lines on either side of the line. Whoops. I'm trying to play only one song because I don't think it'll copyright strike me for it, and it's my favorite song. So this space is one-dimensional, if we're talking about dimension. So space is really important for geometry. All of geometry, when you think about Platonic forms, like Plato and Aristotle and all those people, they talk about Platonic forms, and those are really just forms that are like perfectly defined. But they're only perfectly defined within the certain definition. So if you have the pixels, you can make a perfect square, but the pixel is still making that square. Like this is only a square because it's a pixel. If I make this, then it's a square because it's made of multiple pixels, and the pixels are squares, and the squares combine to make a bigger square. But if I try to make like a triangle, this isn't really a triangle. I can't even make the angle. There's like this jaggedness to the pixels. And you could try to rotate it, but then, yeah, see it like, because it's using this, what is it? It uses these sampling methods when it's converting between the two different forms. I don't want to confuse you too much though. That's getting into like computer graphics, but that's important for understanding like space. If like all of these things that in space that were like kind of these platonic forms, these like perfect things that are like a perfect circle. A perfect circle is just r or like x squared plus y squared equals r squared, and then r is just the radius, which is a measure from here to here. So, and then x is like the xy plane. Let's say this is the 0. You can put the 0 anywhere you want, actually. And so this is x, and this is y. So this is a circle around 0, 0. You could define the point as 0, 0, and maybe this is like -1, +1 kind of thing, you know? So this is 1, this is -1, this is -1, this is 1. So this is a circle around this, and we're saying r equals 1 for this. But that's a definition. You have to use this. You have to relate these variables, and it uses all this function stuff. So we're actually using functions. We're using computation to construct this like perfect geometry, and that's really why it's the only reason why it's perfect is because it's using the function. That's the only reason, because it's defined perfectly. If you have an equilateral triangle, it's defined perfectly as what it is. Even if I do the triangle tool in paint.net here, it's still not perfect. It's still got these diagonal lines that are like pixelated, you know? And you can make vector graphics, and vector graphics are nice because it defines it literally as a point and a line, and it'll automatically scale it, so the pixelation you won't even notice, because as you make it bigger, it'll just, the pixels will stay where they are. Like if you make this, instead of this happening, well, this happens more. Or like if you have a line, god dang it. If you make it bigger, it gets all blurry. But with vector graphics, you could make this perfect because it would automatically compute with a function like the width has to be constant, whatever it's defined as, and the points that it's traveling between are just points in some coordinate space, which is this xy thing that we were talking about, that I was talking about. So let's talk about counting and space, because space is really important, and it is kind of, it's strange, you know? So everything is different because it's in a different place, it's in a different position. You could copy, I can make, what was that? You could copy this. Even, this is a pretty unique shape. It's not like 100% unique because you can copy it. Because somebody else could have accidentally or purposely made the same exact shape somewhere else. Somebody could copy it. Or it could just be like, you know, it's just like, is this a copy of every other shape that has the same pixel layout? No, it just is the same. It's the same. So there's a symmetry between them. There's a symmetry between these two shapes. They're the same, but they're also different. So this is in one location, and this is in another location, or position. You can call it location or position. They're a little bit different. Position might be like more coordinates like this, versus location, I think, is more like, where are you? I'm gonna locate you, or something. But that's just my perception of space having location versus position. Usually they're used the exact same way, and it's like, it's just a coordinate system, and you're saying this is here, and this is here, and this is here, relative to these points that are here, everyone else here, is important. So everyone is different. Everyone in space-time, you could just call it space, but it is space-time because nothing can interact without time. you can't interact without time. So like, if you want to interact with me, you have to like point towards me and like send a message, and then something happens here. Like here you are, and here I am, and you have to send this here, and I have to like be here, or it's like I'm here, just sitting here, and you have to like send me a message, you know. So we have to have time in order to interact. This is where the interaction takes place. Is where these arrows meet. Where the motion, where we meet the same point, you know, like my fingers, they have to interact, and I'll get into that because it's a little weird. Like there's mediation particles, like this will send off a particle, and then the particle will go over here. Particles over here now, and that was like a photon, for example. So the photon came over here, and now it's like it's in here. It caused some effect. Maybe it's not the photon anymore because it like went inside and it's like different. But let's say that does take time. So all these interactions take time. In order to find out where something is located, it takes time. You have to do like a triangulation, like where is it relative to 3 points or something crazy, you know. Some kind of temporal thing with time where you're moving, you know, and so this is the space is like difference. Space is like difference, and time is like change. These are really fundamental similarities between these concepts. I'm proud of that. That's accurate. Because you are in a different location. This is in a different location than this. And the line between them kind of represents their difference. It's like a subtraction symbol. If I have this minus this, you could say they're ones, but you could also say it's like a subtraction symbol between positions, or it's just like a relation between them. It depends how you use it. You know, logic is there's logical systems that work differently, and symbols can be used in many different ways. You can always have like a little accent. Like this isn't actually a triangle. It's an almost triangle. But difference is really important. And then there's sameness. So that's related to identity. So these are the same. These are the same shape because I copied it to make the same shape. These are the same shape because I drew them to be the same shape. I think that's what I did. I don't think I copied it because I drew them like this. See, I'm not copying it. I'm not selecting it like this and copying it. I'm drawing them both the same. They're still the same, so you don't have to copy. You don't have to do that temporal thing of copying in order for it to be the same. But identity, excuse me, identity is different because identity is like uniqueness. So sameness is there. Then there's difference. There's similarity, which you can probably guess what these words mean if you've heard them before. And then there's uniqueness, specificity. So the way I think about this, let's say there's like a bag, and right now, let's just say I'm not counting. This is another thing about counting. We already forgot counting in space-time. I'm just gonna assume you know how to count in space-time. 1, 2, 3, 4, 5, 6, 7, 8. That's how you count in space-time. I just did it. There you go. Now you know. You're counting. But an important thing is how you decide what you're counting. So now you'll get to learn that a little bit more here. So if you're counting triangles, let's put some stuff in here. Let's put a triangle in here. Let's put an upside down. Is it an upside down? I don't know if that's an upside down triangle. Maybe this is an upside down triangle. Let's put circles, triangles, and some squares in here. I'm just making them not exact, but it's fine. Let's call them rectangles instead of squares because they're not really squares, and they're not really circles, but they're like they're like whatever they are, curvy boundaries. They're like circle-ish. But let's call them circles, triangles, and rectangles. So I'm calling them that. I'm choosing to call them that. We do that all the time. That's a really extremely common thing. We call them that because they have some similarity. You could say that things that are the same are similar, but they're exactly similar. They are specifically 100% similar other than their exact uniqueness. And that's the thing about space being different, what I talked about, and the reason why all these different shapes, why they're so important to things, is because their uniqueness tells us what they do, and the shape in our brain that the neural networks make, or the shape that the functions make, is different. And the shape is entirely spatial. Shape is spatial. That's the thing about shape, is it's spatial. When I say shape, or all of these things, well, angle and dimension are different because they could be temporal as well. But shape is spatial. Geometry is spatial. Temporal stuff does affect it though. It's definitely relevant, but space is kind of this thing that allows you to tell the difference between this and this because they're in different positions or locations. So they're different. They're different. But they are similar. They look similar just at a glance when you look at them. And if you identify every single pixel exactly, which might take some time because it's a little irregular, you would find that they're exactly the same, other than where they are on the screen, where they are on the space, in space. So space is kind of this thing that you come back to when you want to say it's still different because it's in a different location. It's still because space provides that difference. And a lot of the time we use that difference in space to make logic happen. So if you've got like a switch, for example, and you want it to disconnect, you make this thing go over here, and then you want it to connect, you can say, there's joints here, there's things here. So these are joints, and then you can snap the switch back in place, and now it connects, and now electricity can flow there. You could make it yellowish electricity. Whatever the fuck electricity is, it doesn't have a color. Electromagnetic color is electromagnetism, but electromagnetism is not color. Because light waves have a wavelength. Sorry. Light waves have sine waves. So that's one way that. So that's an important thing. Is there's this. How does sound work? I think sound. It stays on a minimum. So light is kind of more around a center like this, and sound is like this. So this is pressure. And then this is actually, you can't really, this is air pressure, which I'll get into later. It's just like, it's something that emerges out of things like causing force, like on a wall, for example, or a surface. So if you've got like a bunch of particles and they're all hitting this wall, there's a certain amount of pressure there, or they would be going up in this case, I guess, if there's more of them. So this is kind of like the amount of force. And this could be space or time. Let me see if I can get, I have a helpful image for this. What was I gonna say? This diagram, someone else's diagram on like Wikipedia, it was. Let me see if I can find it really quick. Here it is. It's called a commutative diagram of harmonic wave properties. Commutative diagram of harmonic, what was it? Wave properties. And when they say property, they don't mean like ownership of like external things. They're talking about like something that can be computed or calculated from the wave. So the wave here, let's look at this, because this is a really important thing for space and time too. So this is a spatial dimension. This is not spatial or temporal. This is a temporal dimension. 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 So these wavelengths, they're spatial. They're spatial here. And the frequency and period, frequency is like if you select like a single point in space. That's the thing about it, is the frequency, it depends on how you're measuring it. whether it's like with angles or like a spatial distance. So like how many waves there are in this space, in this distance. Well, there's 1, 2, 3, 4, 5, 6, 7 peaks, and 1, 2, 3, 4, 5, 6, 7 troughs is the word they use for that. So you could say there's 7 waves, or the frequency is 7 within that space. But then there's also the number, or sorry, that's like the linear wave number, I think, actually. That's the number of waves that appear in a single space. But then there's linear frequency, which is, I'm not sure. It's kind of tiring. I really don't like the way they visualize it. They don't put units, they don't put like time or space, they just make it pain in the ass. I'm just gonna ignore them because it's really dumb. But you can think of it like if you're like sitting in one place, let's say I've got like a hole and then some light waves come through it, or some photons come through it, or some air particles come through it. And so you're counting, that's kind of counting, count how many particles pass through. And that's kind of quantum mechanical experiments. You're counting how many things go through the hole. Sometimes you don't know though. Like I don't know how many fucking people have seen or copied my stuff. That I am still slightly modifying, even though it's mostly good and correct and accurate. But when I say that, I do kind of mean for you to interpret it yourself rather than to believe in rules that I constructed. Like this is the definition of a circle, or a definition of a circle using X and Y and R, but R is necessary. This is required. It doesn't have to be an R. It could be any variable name, but it's still R. Oh my god, I didn't explain variables. That's okay. We'll get to it. Let's talk about the counting thing. So there's sameness, difference, uniqueness, and specificity. So we're going to use similarity to count things on both of these things, in both of these boundaries, this left boundary and this right boundary. So I'm going to say count triangles that are pointing up. No, let's just count all squares actually, or all circles. So 1, 2, 3. There's 3 of them. So I draw a line to them, and then I say they're all, I counted them, and when you add them up, there's 3 of the same shape. And when I say same, I'm actually kind of lying to you. I'm saying the same shape, but it's not exactly the same. They've just got similarity to them, so I call them the same shape. So the shape is kind of this broader thing that you say like this is a square, and this is a square. They're both people, or they're both squares, no matter what size they are. And that's kind of similarities, even though they're the same shape, even though they have like certain characteristics about them. When you look at them, when you perceive them, and you view certain dimensions about them, that's what dimension is extension, I guess. Maybe that's a good way to think of dimension. Is space or time. But it could also be like something that you construct out of both condition, case. And that's like if-then statements. But I'll talk about that later when I talk about computation more specifically. But I will talk about it, and it is kind of relevant to this. But even see, it's kind of like I'm trying. The part about counting is it's very difficult to count things if you don't know what you're counting. If you know how to count, and you can say this is a square or a rectangle, this is a rectangle, this is a rectangle, you could say 1, 1, 2, 3, 1, 2, 3, 1, 2, 3. It's 3. You know, I can keep drawing it separate places, but it's still 3. There's 3 of the similar shapes. They've got 4 sides. That's what a rectangle is. Or they've got 4 sides, and it's a quadrilateral. That's the real word for it. There's quadrilateral. I'm not going to get into every shape. You could look it up on Wikipedia. there's different shapes. I don't know what I'm deleting now. Fuck. Okay, I have to leave that now. I'm gonna get rid of these though. This is here though for whatever reason. No, I can get rid of it because it's not touching it, and I know the difference because they're not touching it. Because they've got empty space where the black background is showing through. Beautiful black background, beautiful white lines. It's just contrasts. So that's kind of an important part of that as well, is these contrasts. The only reason why anything is visible is because there's a contrast. Something is there, the light wave. So there's a wavelength. This is like a wavelength, is from one peak to another peak. And that could be, what do I say, like a period as well. A period is basically a temporal wavelength. So the period and the wavelength go together by the velocity, or the phase velocity. There's different kinds of velocities with waves, so it can be a little confusing. And it's kind of like what is actually moving. Certain things aren't actually moving with the wave. So certain things can move faster than the wave, apparently. Like a shadow, for example. I'll get into that. It's kind of interesting. It's like, if these are light waves, they have to move at the speed of light, but then this hits a barrier, so this is moving here, and this is moving here. So there's a shadow here, the light doesn't move here, and if you rotate the beam of light that you have a beam of light coming out of here, this is a light source right here. If you rotate the direction that it's pointing, then the shadow will move at faster than the speed of light. But the light beams that are moving out this way will not move any faster than the speed of light. I learned that online from, I can't remember his name. But yeah, it's a shadow, like eclipses. So an important part of space and time and this conditioned case thing is this like intensity. Pressure is an intensity of interaction with like a wall or whatever, a surface, some kind of surface that there's a pressure against my hand. There's a pressure of the air on the moon against the surface of the moon, but it's a lot less than the stuff on Earth. It's like 1,000 times less, probably less than that, because the amount of air that's being gravitationally pulled down is a lot less than, the amount of air that's there and moving. That's what really matters to pressure, is there's this velocity, and then there's something that it's pressing against something. So there is force. It's force divided by area. That's pressure. That's the calculation for pressure. And force, we'll realize, is an integration of interactions, but that's kind of also its own thing. But this you could say is a light wave, but then there's also like, there's this weird thing where it's got two dimensions to it. There's electrical and magnetic fields, electromagnetic waves, light. So these are all the same thing. You could think of each of these two different curves as like electrical versus magnetic, but I can't really visualize it very well here. And you can't really visualize it very well at all, other than like this anyway. This is just kind of what it looks like when you do it. Like, this is like electricity, or what is it? That's the electrical field. I don't know if that's charge or what. Let's just say that's the electrical field. I forget what, there might be a letter for it, but let's just say it's M and this is E. Me. That's you. Me. Matter and energy. M and E. E and M. Electricity and magnetism. It's a good class. E and M is a good class. So this is just a way to understand, like, when the point is up here, that means it has more electrical field or more magnetic field. Although they can have direction to them. So they could be, they could have a direction to them, or they could just be an amount, like a quantity. So that's what's a number of dimensions. So the number of dimensions of things is an extremely important thing. If you've got a one-dimensional thing, it's like a line, and you can just jump up and down it. But if you've got a two-dimensional thing, then you can have like parametric equations that go all over loop-de-loop place. And then if you've got three-dimensional stuff, you can have like a sphere, and it can like have a coordinate singularity up at the poles where it's like you can go around the longitude and latitude, like I forget which one's which. I always forget the difference between longitude and latitude. But up here, you can like pass through multiple of these up and down lines. You can pass through many of these north-south lines over and over really quickly up at these poles, or at the bottom pole, the south pole, or you could flip it. It's the same thing. It's a perspective thing. That looks like an onion, kind of. It's just like a grid around a. It's a grid wrapped around a sphere, but I can't draw a sphere very well. But the number of dimensions, if this is 1, let's 1, 2, 2D, 3D. I think we all kind of know that. Then there's like 4 plus, and time is kind of like related to that, because if you want to count time, you have to understand that it's not one of the 3 spatial dimensions. I'm 3-dimensional. I can rotate pi radians. I can look at that holo pillow that I have. I could tell you about it, but I'm not going to. I could show you my my holo figurine. It's pretty cute. Or my Moto figurines. Yeah, that's just anyway. So let's move on. So let's talk about how you're counting. This is, I think this, like all of this is actually really interesting and important. I'm gonna get rid of these though, because they're not like, this is light and this is sound. It's a pressure wave, and it could be space or time. It's really just extension. That's kind of the weird thing about it, is it's really just extension. If you want to understand it, it's just extension, because it's moving through space. If you want to measure it, I guess I shouldn't, it's not that obvious. If you want to measure the wave, you have to let it go into your eye or some other measurement, or your ear, and it has to like cause some interaction. Maybe it causes some interaction here. I don't know what's happening here. Something happens, an event happens, some change happens to something other than just the wave. It's not just passing through space, it hits something. And that interaction is what you're actually measuring. So this pressure is pressure against like the drums of your ears, right? People often know that, but it's not the most well-known thing, and it can be kind of complicated. It is complicated. But if you think about what you're counting things, so if you have space-time and you're trying to count things, you count the number of sound waves or the number of light waves that have gone through, or count the wavelength or the period or the frequency or the wave number, you have an experiment that's counting that. And you could have some conditions or cases that you take and you say, oh, I'm not going to count that, but that's your choice. You're the experimenter, you're the scientist, you're the living thing that's making choices about how you're going to interact with things that you call an experiment. You're calling it an experiment, but you're still doing things. I could shoot somebody and call it an experiment, but I'm still shooting them, you know? You're still doing the things that you're doing, regardless of whether you call it an experiment. You're still measuring it. You're still converting the sound waves that I'm sending you. Bah! It was loud. That was a loud one. Bah! That was not as loud. Blah! That was like kind of quiet. So you could have it. This is obviously not the graph of what I just said. Excuse me. But it is an example. This is like a pain in the ass because you don't actually usually care about the difference between the electrical and the magnetic fields. What you really care about is the linear wavelength, or maybe the angular wavelength. Maybe that's somehow relevant to it. I'm not sure. Maybe that's why color is a thing. Who knows? That could be really interesting. I just thought of that. But usually when we talk about light and we talk about color, we talk about its linear wavelength, But angular wavelength would have to be compared to some radius, so you would know like the radius, like as it's how many times it's wrapping around this or something with its wavelength. And the wavelength is a length, so it's a one-dimensional spatial quantity. That's what length is. It's a one-dimensional spatial quantity. I talked about this in a previous draft of this, but I'm going to talk about this really quick because this is really important to this, but it's also like kind of a pain in the ass. But I'll talk about it as well with this when I move on to that. Oh my goodness, God, there's a lot of stuff to talk about. Continuous, and I do want to explain the difference between continuous and discrete though. So this continuous, let's say this is discrete. So this is 0, 1, and 2. So there's like 0, 1, oh wait, sorry. 0 doesn't have anything. There's nothing there. And 2. So you're not 0 because you have stuff. You're a 1. There's stuff there. That's why I like this. But this, real numbers are weird because let's just ignore that let's put it at 2. It doesn't matter if it's 2. Sorry, that can be 0 as well. It can be the same. It could line up. It doesn't have to line up. I'm just doing that to make it kind of easier to understand. So this is a half. Now this is a half. This is a rational number. Rational numbers can be fractions. They can be dividing 1 over 2. So it's like a pie, but only half is filled in. So it's kind of like that in comparison to this. So this would be like some kind of weird thing where these are there's a few different kinds of numbers. There's whole numbers. The main difference is the discrete or continuous. That's the main thing you want to remember, is the difference between continuous and discrete. So this is continuous, or this is discrete, and this is continuous, because there can be fractions. So fractions are rational numbers, but you could also just keep dividing it in half, and you could put pi here, you could make it go to 3, you could put e here, 2 point, e is around here, this is 3, and pi is around here. Pi is like 3.14 ... It's an infinite number. It has infinitely many digits, so it's irrational. There's no fraction that you can use to represent it. And that's why it's not just rational numbers. So the continuous has all these different things. The continuous contains the whole numbers, which is like these. It also contains 0. 0 is actually I think these are natural numbers is what they call them, and then 0 is a whole number. I can't remember. I always mix them up. It doesn't make any sense to me. Natural is like a fake number. They made that up to make you lose. Excuse me, you're not retarded. Everybody's slow at everything. But it's like, it's just like they just make up words. All words are made up. Everything is made up. Like everything is exactly what it is. So when they say like natural versus whole numbers, what they're really talking about is whether you include 0 or not. That's literally all they're talking about. You could call it 0 numbers versus non-zero numbers or something like that. It would still be the same exact thing. I don't understand it. I never remember the difference because it doesn't make sense to me. It's not intuitive, so I hate it. I just let it rot. That's how you can do things when things aren't intuitive and they don't even work. Because it's not even relevant too. The name is not relevant to the thing. All these names, all these words, sameness, difference, similarity, specificity, count, pressure, all these words, they're all made up. We made them up. They're fiction. Well, it's not the same thing as fiction. Fiction is like depicting, representing things that are not real, but they are kind of fiction in that way. Numbers are fictions, but they do correspond to things, so they're like non-fiction when they correspond. But that's like the whole thing about truth, is you're counting things. Let's say I wanted to count like how many pixels there are. They're exactly the same. Or let's say I wanted to see if there was only this specific shape. I don't know what I'm doing. But you would do some kind of interaction between these two. You would be using this relation between these two boundaries in order to access that space. So this difference, this space, the line between things is acting like a space. Space is line and time is arrow. That's really, when you get down to it, that's the truth. That's the truth. Space is a line and time is an arrow, and everything else is just stuff based off of that. And dots, pixels, they're not real. They're just squares because you have an area. If you really want to talk about units, what you're really talking about is either space or time, or the things in space-time, which is like pressure. So pressure is stuff that's moving. So this is like an air molecule. So it's made of electrons, protons, and neutrons. I'll get into that later. There's fundamental quantum particles, and atoms are made of electrons, protons, and neutrons. Most people have heard of that. Not everybody. Most people have heard of like everything here, but they don't know it very well. So that's kind of why I'm still talking about it. I apologize for saying that earlier. That was uncalled for. This is all, I just get frustrated because it's like, it's obvious, but it's not. And people like to say the words instead of explaining the things, and the words are not the point. The words have absolutely nothing to do with the actual topic most of the time. You can't even like find an like I try to think about like the letters being used, and it's like, oh, that's kind of a funny pun or something, but it's not like like this is the number line. Like if I write number line, like what language? This is English, you know? This is English. English isn't special. Fuck English. But like I said, so this is what they call them, is real numbers, and then this is for continuous versus discrete. Let's move 1D up here. 1D, all of these dimensions, they can be either continuous or discrete. So like space is continuous 3D. It's continuous 3D, but the pixels here are discrete because they're like squares. And let me so the main difference between these is they're separate. So they're entirely separate, and there's no space between them. So these like dotted lines that are being rendered, they're being rendered on our screens. They're being added later on, but if you like look really closely at your screen, you can still see the pixels. We don't have screens that are like I can still see the pixels excuse me on my screen, and those pixels are little units that are sending out these light waves, and the wavelength between two peaks or 2 points or 2 troughs or whatever, the wavelength tells you the color of the light. Do I have an image for that? That's like a free easy one. Fuck, I don't have one. Whatever. Colors are here, I guess. So it starts with red. Fuck. Forget all this other shit. Let's just put big rainbow over everything. Shit. Let's put a rainbow over everything, and I'm going to explain that to you. So red is a small wavelength, or sorry, large wavelength, but small frequency. Large wavelength. So these two wavelengths will be large, but the frequencies will be small. So how many waves you get in 1 unit of time? So like if you, like if I say from here to here, how many waves are there? And then you divide it by the amount of space, then you get the frequency, because it's the number of waves divided by the amount of space that the waves are in. It's that frequent, you know. There's temporal frequency as well, and that's kind of what we're really talking about. But you could talk about frequency in spatial or temporal things, because we're really talking about extension. Like all this stuff velocity is how space and time interact, and that's kind of like what time is velocity. So you can't really have space without, or you can't have time without space. Space without time, however, that's another thing. Let me explain this, because I was trying to explain this in another video and I got frustrated because it's like a pain in the ass. It is a pain in the ass. 400. So space, time, sorry, no space, time, no time. Space, time. So this is space, time. Sorry, the table's kind of funky. No space and time. No. No. These things don't exist. I'm just going to say those don't exist. This is like platonic forms geometry. They call it platonic forms, but it's really just geometry. That's really what it is. It's like these eternal concepts, like an equilateral triangle. It doesn't tell you how big the triangle is, but it does have space. And that's another thing about space, is you're comparing it between spaces. So if you want to say something is 2 meters long, what you're really saying is it's 2 times as long as this other thing. So this is a meter, and this is 2 meter, m. This is an m, or a meter. This is 2 meters. So you're comparing it between the two. What you're really saying is this length right here is the same as this length. They're identical distance. When we talk about distance, we're just saying that it's the same absence of stuff, I guess. Like a distance is just how much space there is. It's a quantity of space. So you're counting space, but you're counting space using stuff in space. So what you're really counting is the stuff that has space to it. So this is a stick, this is a line. The line has space to it. There's a spatialness to it. And when you measure it with pixels, because I drew it in pixels, that's how it exists here, it says 55 here. So the width is 55, or if you get rid of the these things, it's diagonal a little bit. So you kind of, it's like where you measure it from. Do you measure it diagonally from here to here? I don't know. However you measure it, let's do that. Let's measure it discretely. So continuous measurement, trying to measure the continuous is kind of like impossible. Like how do you measure only a tiny amount, but not any more, and not too little and not too much? And how do you keep reducing that amount until it's smaller, and so you know that you can keep dividing it so that you know it's actually continuous? Because this is fundamentally different than discrete. It's fundamentally different. But these pixels that I have, 1, 2, 3, 4, 5, when you're drawing a line, for example, what you're really doing is counting how many pixels it passes by, how many pixels it fills up. So this pixel's filled, this pixel's filled, this pixel's filled. Like this horizontal position, you know what I mean? Like, let's put it this way. All of these vertical lines are a vertical position that's being filled by this line. So if you count up how many are here, you know the width of this line, because you know how many pixels wide it is, how many pixels are in it. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. You can count it however you want. You just go anywhere you want. So it's 9 wide, and of course you can count it. You could go. You could even say 1, 2, 3, 4, 5, 6, 7, 8, 9, and kind of count it that way with your brain. But you're counting things. You're counting the space using the discrete pieces that it's split into. And that's the thing about space, is space isn't actually divided that way. It's all together. Space is all actually this one giant space. Everything is in one space. Everything is in space. This is in space. I could show you the stream, but I'm not going to because it'd be a pain. It'd just be kind of, I don't want to like put it back. I have to put it back and reposition it at all. And like confuse you. But it would be like, everything is in the same space, and space is continuous. But when you want to count how far something is away from something else, you have to use something discrete like this. You have to use a line between them, and then you count how many pixels it goes through, how many pixels it fills in, like these are being used to illustrate. They line up just like that, and you count how many it goes to. So these two are very related. You use discrete to count the continuous. Like I said, with like a meter, you could say a meter is a pixel, or a pixel is a meter by a meter, because a pixel is two-dimensional. So a pixel is two-dimensional, whereas this is this, and this is like, so this is a cube, yeah. This is when you have perpendicularity. So perpendicularity is right angles, and that's 90 degrees, or, you know, like a square. I don't know if you're familiar with that, probably, almost certainly. But that is geometry. This is how they're split up. There you go. I separated it for you. Let's make it a different color, if it'll work. Look, I can fill it in, and because it's all connected, because there's no space where there's absence between, or transparency is what this program is using actually, because the black background is just there everywhere. The transparency here, there's nothing here on this layer, so this layer isn't being shown or rendered. Yeah, these are the number of dimensions that we are commonly used to. So one dimension is where you start, because that's like more than zero dimension. 0D is just a point. That one's kind of boring. I don't know what to say about that. That's just a point. There's no dimension to it. It's just a point. It's a pixel. It's technically 2D, but you have to believe me. It's zero dimensional. You have to. You have to believe me. Maybe you don't, though. Maybe you don't believe me. That's okay, though. But it's supposed to be a point as opposed to a line. And then this is like a square, and this is like a sphere, and this is like a cube. I think I kind of explained everything here. Continuous and discrete is really important. Continuous is kind of like death, because it's like, and space is like death, and well, space-time is like death, because where does it go? It's got that infinity to it, that infinite absence, that infinite nothing of space. Like where do things go? It goes into the infinite nothing over here. This is over here, like it's infinite because it's everywhere. It just keeps going, and you can keep like inching it little bits and bits further. You could say everything's discrete, but there's no proof of that. And what is its shape? I don't know. Nobody knows its shape. And then there's like black holes and weird shit. Anyways. Okay. Let's take a water break, and I'm gonna think about, we're gonna move on. We're gonna move on. I think I've talked about this fairly a lot. This is kind of, I'm gonna continue to say this. If you don't have space, what is changing? Time is like change, right? Things are changing, something is changing, and what change means is that it was one way before, it was the same as itself, everything is the same as itself. I am myself. That's what sameness can be. You are identical. I guess identity is kind of like that. So identity is when something is itself. It's identical with itself. That is what it is. It is what it is, you know? That's what its identity is. Sameness uses that, but it's also its uniqueness. And then difference and similarity are kind of special, and then there's specificity. I'm not sure how to explain that. If you look up the words, you'll get it though. This is really fundamental. I'll explain it like really quickly. Just like define each one separately, because trying to relate them makes me really confused, because they're very important and very big. This too. So sameness, two things are the same if there's no differences between them. And a difference is something that you can tell apart. You can tell the difference, that there's a difference. They don't look the same, they don't sound the same, they're not in the same position, That's a difference. That is a difference. Spatial positioning is different. Time is also a difference. So time kind of, maybe that's why I think this, is because time has this line to it. The arrow is made of lines, right? There's this line, and this line. It's made of, we draw it with space, and it moves through space. That's the only way that we know there's time, is because it moves through space. So the change is space, like the change is occurring to the spatial position of the things. So the things are changing where they are, which is their spatial position. And their spatial position, you could say, is relative to one another, but there's also like centers of momentum and conserved quantities, and I'm not sure if centers of momentum are conserved or not. But conserved quantities are things that remain the same regardless of the change. So whatever change or difference there is, change and difference is kind of very, very related. A change is a difference between the past and the future. So it's the difference between the past and the future. So this is like this, and this is like a square. The change is that it went from a circle to a square. That's the change. Change. I can't draw or write. And then similarity is when some things about it are the same. Like say there's somebody else with brown hair, or similar like that. But we're not the same. Maybe you know all the number of polygons because you understand that it's like this, you know, you can just keep drawing numbers of sides, and the number of sides is the number of lines that you need to draw it, and the lines are generally relatively straight. They're not like curved like I'm doing, because I'm just going quickly. You can tell what it is, and I could get into the geometry of angles and lengths, I guess. That is relevant. I wonder how long this is so far. I don't know. So let me finish this first, though. So similarity is when things have something in common. When some subset, like these two, this is similar to this. This boundary is similar to this because they both contain triangles, they both contain rectangles, and they both contain circles. They're not perfect. They're not actually what I called them. They're not actually triangles, circles, and rectangles. They're just close enough for me to call them that. You can't even draw a perfect triangle or circle in pixels. It's just not the way it works. You can use vector graphics, but that's different. Vector graphics uses... God, vectors are also a thing. There's so many things to explain. Oh my goodness. Shape. Angle. These are polygons. It's the number of sides. This is a side, is a line. You could fill them in and there's still a polygon. So you could say they're like different styles or different rendering methods or operations or functions. The way that I drew it is different, but it's still the same shape. So we say it's the same shape. Sorry. We say it's the same shape. You could do that. We say it's the same. Oh yeah, and you can have a circle too. That's like infinite sides, but that's not really, you can't draw the perfect circle because it's really like pixelated. And what you're really doing is you're just trying to follow this equation if you're trying to draw a circle. All circles are this equation. But yeah, these dots, it's a different way of drawing it, but it still kind of follows the same lines. It's like you can draw the lines over the dots and it doesn't make any difference because the lines were within where the lines would be. Excuse me. So if you have a line, like it's a gapped line, but it's still a line because you can draw the line through it, and there's it's made of lines. If it was made of dots, that's not a line, that's a bunch of dots. But you could say it's a line of dots, and you could just kind of tell people to treat it that way. You could tell people to process it, to operate on it that way, to interpret it that way, that it's a line, even though it's a bunch of dots. Whereas with a dashed line like this, where each little piece is a unit, is a dash, these are lines, or rectangles, or whatever you want to call them. Lines are kind of like rectangles, although sometimes they're like weird like that, where they're like aliased, anti-aliased. They kind of, you don't know what to do about when they do that. Maybe you do this, maybe do this, maybe do this, maybe do this, I don't know. But this is a little more obviously a gapped line, whereas this is kind of like, it looks like it because there's nothing around it, but if I start doing this doesn't look like a line anymore. It just looks like some weird fuzz. Maybe it looks like it's got a line here that it's like not able to go through unless I like start putting dots up there. You're thinking about like a wall, you know? Thinking about stuff in space-time. That's what you're talking about all the fucking time. Every single fucking time, you're always talking about stuff in space-time. Everything. Sameness. And this is like related to symmetry and asymmetry. You could even say that they're like synonyms. Symmetry is a sameness. Well, but they're like, they're not synonyms. A symmetry is a sameness with a difference. So it would be like a symmetry is a similarity, I think. Yeah, a symmetry is a similarity, and an asymmetry is a difference. So this is like a asymmetry. This is an asymmetry, and this is a symmetry. So there's a symmetry between these because even though they're curved, I'm just gonna, like, you can still tell that these are lines because they're like roughly straight. Like they still like, they have this angle to them. Maybe that's it. Maybe that's the point. How many angles are there? Each angle is made of two lines here and here. And that's how you tell how many, like I could do this, I could make it a triangle, or I could make it a quadrilateral, so it's got four sides, or I could make you confused by doing that, and then you don't know what it is because it's like some weird fucking thing on the bottom. But this is like a line that's being used as a side of the shape. And you can, then you can fill it in if you want, but it's still like, you know, that's still fundamentally similar. Sorry if that, I hope that doesn't cause you problems. But yeah, an angle is two lines connected at a point. Maybe the angle doesn't actually meet. Maybe it's like this, and then you're like implying that there's a line, and then it meets somewhere here, but there's still an angle, you know? There's still an angle here. This is where the angle is, but it's between these two, so it's like it looks like a Wi-Fi symbol, or this is really common, is people will do this, or if it's a right angle, if it's like literally exactly perfectly like that, they'll do this to say, oh, it's a right angle, and they might even make it like a perfect square. And now it's a square, and this is supposed to represent or tell you, even though it's an extra thing, it's supposed to represent or tell you that this is a right angle, that it's a 90-degree angle, versus 360, which is all of a circle, going all the way around from here to here to here to here. It's quarters of a rotation, you know, because you go like here. That's an important transformation, is rotation. So each rotation takes 90 degrees. And degrees is just a way of measuring angles. You can also use radians. So a radian would be like, if there's a radius r, then the circumference is 2 pi r, and this angle is a number of radians equal to the arc length that it traces out, so this only divided by this. Something like that. I don't know. It's related to the radius. It doesn't matter. It's just proportions of a circle, of a rotation. That's what it is. It's rotations. That's what angles are, is rotation. Because you're going from here to here, or from here to here. It's either way. So that's kind of how you can tell that these are triangles or square or rectangles. I mean, even though they're not perfect, even though these are not actually lines, they're curves. That's the difference between a line and a curve. This, maybe even if it's got two, if it's like thick like this is a rectangle, right? You could hollow this out. That's a rectangle. But you could still call it a line. It's a line that is a rectangle. And then, but you can make it a curve instead. You can make it kind of curvy. And that's like different, because that could be like a x squared function or something. Or it could just be a sine wave, or any kind of curve that's not perfectly straight. And perfectly straight just means it keeps going in the same direction. I just figured that out. I've never thought of that before. Non-curviness or straightness is just having the same velocity consistently and not having it vary at all. That never happens though. That literally never happens because of quantum mechanics. So that's kind of like, yeah. But it might happen close enough in your measurements, you know, because you're only measuring like, if it fits within here, you're gonna call it 1, even though it's like 0.99 or something. If it fits within here, you're gonna call it 2, even though it's like 1.99 or whatever. So it's close enough. The degree of uncertainty is also a really important topic. The degree of uncertainty is less. Okay, what are we gonna talk about next? I feel I need to pause. Let's see if I can pause this. I'll be right back. Hello? Test? Hello, I'm back. So, let's go over this really quickly, because that was the first. I kind of explained what continuous and discrete was, but I didn't explain calculus and graphs. I will. They are really important. And then I'll start getting into physics more completely. I'm not going to tell you all the physics equations. That's not what I'm trying to do. I'm going to give you a gist of it. I'm going to give you an understanding of it distilled, rather than just being like, you have to memorize all these things. I could give you a cheat sheet. I don't have a cheat sheet. That would be nice. Nobody does that because they're all assholes. They're all little assholes trying to get money. But yeah, we could have a cheat sheet for all of physics, but that's not what they want. They want you to go to school and pay money to a university that's going to overcharge you, when you could go to community college, or you could just learn it through online resources that are open source or free, somehow free. I would recommend, I'm going to keep doing this forever, alternative2.net. Wikipedia is okay, but look at sources. PBS Spacetime is really good. Feynman's lectures are also really, really good. These are really good for physics. PBS Infinite Series is really good for math. And then alternative to Wikipedia are just really generally good. Wikipedia is just really, really generally good for kind of getting a gist of information. Wiktionary is also really good if you just want to know definitions, like a dictionary. And then alternative 2 is really good for getting software if you want to get free open source software, or find somewhere that will give you educational materials. That would be awesome. Okay. Next, I think we understand counting. Let me finish this. So asymmetry and symmetry are in or related to very closely to these two things. Uniqueness, I would say, I don't know why, like, I feel like these are different than these, but I don't know why. Identity is basically, let's start with uniqueness. Or let's start with specificity. So this has specifically these shapes inside of it. Actually, let's erase them and remake it, because I'm not you with it right now. So let's put a triangle, a square, and a circle, and a triangle, a circle, and another triangle. So these have similarities, but they're completely unique. They're not completely unique. Nothing is completely unique because everything has something in common. Everything has certain symmetries, and that's kind of what the holoscope stuff is about, is finding symmetries that everything has. Although the words might not be perfect, even in English. That's funny. So, yeah, in English, that is an interesting way to think of it. It's a condition. You're using English. You're in English. This is, the word condition is in English. But let's talk about this. So specificity, specifically, there's a triangle here, and a circle here. And specifically, there's a square here, or a rectangle, you could say. Maybe it's not exactly square enough. You wouldn't be able to measure it though, because it's not a rectangle either. These aren't actually, I'm just calling them that because they're close enough, even though they're curves. I can't act, like I don't have vector graphics. I can't draw with vector graphics easily. That would be a pain in the ass. I'm not gonna pull out Adobe Illustrator and start drawing with vector graphics. Even if I use the line tool, it's still gonna have this, and that's gonna piss me off. So I just want you to know, it doesn't matter. It's still a triangle or a rectangle. Enough. But it's not like exact, you know? There's no such thing as an exact one. That's just the truth, because space-time curves. Everything is curved a little bit. Even these pixels, even these 2 pixels, there's a little curve between them because of gravity, because of weird forces going on. Which one? I don't know. There's a curve though, I promise you. Depends on your perspective. So this is a triangle, this is a circle. I'm just gonna call them that even if they're not. So specifically, they have things inside of them, and those things are uniquely what they are. But they are uniquely what they are. Like, they are the only thing that is what they are, because they are where they are and when they are. The where and the when makes everything unique, because without where and when, 2 things that are exactly the same, like 2 electrons in 2 different positions, like an electron in this finger and an electron in this finger, they're completely exactly identical. The only difference is their position and momentum. So their identity is related, they have the sameness. I mean, I think that might be really closely related. Identity is sameness. So the electrons are the same inside, but their identity is not the same because they're in different positions. Because you can still tell them apart. There is something outside of them that can still tell them as different. If you start to have quantum systems, this is a really interesting topic. If you start to have quantum systems where things occupy the same state, and because they don't follow the Pauli exclusion principle, so they're not exclusive. You can have a pixel here, and then you can have another pixel here, and they're in the same position. It's like they're in 2 different layers, except there's no layer. It's not even a layer, it's just in the same position. It's just, they're all there. So when you get to that point, then it's like, well, actually, what we're doing is talking about things that are completely identical. Like, it's exactly identical. It's just there's more of them. There's multiple of them. So that gets into quantum probability theory, and that's kind of weird. But it's still fundamentally from this basic, fundamental metaphysical quality or of identity. Like, it is what it is. I don't know. I don't know. If you can tell a difference, then, like, let me say this. So similarity is like a subset of sameness, kind of. Like, if 2 things are exactly similar, like everything about them, well, no, that's not true. I don't know. Similarity and symmetry are kind of weird. It's like, nothing is exactly the same. Well, except for those particles, they're in the same position. Oh my god, this is actually like making my brain break. I'm figuring this out with you, and I'm wasting your time with it. Thank you. I'm sorry, I'm gonna move on. I think you know what these words mean, though. Everything is unique. it has its own specificity. Some of the specificities have similarities between them, or some of the specificities are the same. So let's say this is the same as this. They're the same. So now they have a similarity between these two because, excuse me, because of this. So there's a similarity. This is a similarity because they're the same, but they're in different positions. I don't know how to say that. Like, they're same, but they're also different. That's the thing that you have to understand, is things can be the same, but they're also different. Like, it's the same electron, but it's a different position. And the uniqueness includes the position. It includes where it is relative to everything else. And that is used for a lot of different abstract things, like if you want to make a shape out of pixels, right? Okay, have I covered everything here enough to move on? These are really important fundamental topics, so don't feel sorry if you feel a little slow or confused by them, even if there's something that we experience every single day. I'm confused by it all the time. And I think everybody is all the time, or they wouldn't be doing what they're doing. Ranked choice voting. So, would make it so you don't have to only vote for the same two goddamn fascist parties over and over. All right, we're gonna keep on the topic. Is there anything else here that I want to talk about? Functions and logic are different. I might start talking about this. This is all this is like something special. Oh, whoops. 800 by 800, let's do. I like black background, it's less strain on the eyes. Night mode. Okay, I want to go fast on this, but I can't. Maybe I will stop the video here and I will make another quick video about this topic, and then I will start talking about these other two large groups of topics. But I'm pretty sure that these are the topics that I want to cover. This I've already started to talk about. This is a function, or well, an equation is not a function. I'll talk about that. An equation is two ways, but a function is one way. So it's a one-way arrow versus a two-way arrow equals versus f. That's an f, not an x. Anyways, these can get very complicated, but they're really not complicated if you start to just like have a intuition for them. I wonder if I should. I'm gonna pause the video and then come back, and I'm gonna decide if I want to talk about this in this video or not. All right, I've decided I'm gonna keep talking in this video, and today is gonna be the greatest video of all time because I'm gonna explain how to visualize a function with my holoscope stuff, because it's a pain in the ass and I hate it. And it's really simple actually. So functions, logic, and computation. So let's draw a function. Let's start with y equals 2x. And sometimes people put a dot there to mean multiply, which is kind of funny. But usually the multiplication is kind of, let's say 2 plus x. Or let's not use x and y. X and y look dumb. They look like multiplication. A equals 2 times, see that's a multiplication, 2 times b. So this is an equation, it's not a function. An equation has an equal sign there, and both sides are said to be equal to one another. So you could say they have a sameness to them based on what the variables in them are. So this is the other thing about these functions is variable types, and that's partly why I explained all of this stuff, is so that you can understand variable types better, because it's really confusing if you just rush into it. I mean, counting is very obvious. You can have integers go like -1, 0, 1, and then floating point can go like -1, -0.5, 0, 0.5, 1. And the floating point tries to be continuous, but it's not. The floating point is basically using the power of scientific notation, like 5 times 10 to the power of -5. So this is like, I don't know, 0.005, something like that. I think this is probably, I think these are equal numbers. If you don't know what numbers are, then if you don't know what these number signs are, then I don't know what to do. These are equal. If you don't know what 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 equals, like is, like it's not equal to anything. But if you don't know what those numbers are, then yeah, I guess that's kind of a problem. But yeah, it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. It just keeps going infinitely. Like this just keeps going if you keep adding them. And the same thing with this, you could just keep adding and you could have 3 and so on. But scientific notation is used for these floating point numbers. So that's one type of variable, and then there's integers. Integers. So these are discrete. But approximate continuous more because they use exponential scaling. Because what you're doing is you're storing in these are the parts that are in the computer with a floating point number, is this 5 and this 5. So all you have to know for the floating point number is maybe it's like 2.6 times 10 to the power of 2. So that's 2.6 times 100 equals 260. So you can use this and the fact that we're using base 10 because there's no number after 9 unless you want to go like A, B, or C or whatever, or you want to make up your own symbols, which I've tried to do, but it doesn't really look that good. Or it's not very familiar, at least. Maybe there's a good way to do it, but I don't exactly love Latin numerals either. They're just fine. They work. They're pretty cool, I guess. I think these are Latin numerals. Maybe Roman. No, Roman numerals are I, V, I kind of stuff for X. And they've got the lines above them. Kind of crazy. But yeah, this is floating point. It basically uses scientific notation, but there's a limit to what can be stored here and here. This is never stored. You don't have to store this because this is always the same. It's a symmetry about the data type. All floating point numbers have that symmetry where the 10 is the same, or maybe it's a different base. You could use a different base. You could make your own data type with your own code with bits to do that. I am talking about variables though. Variables are necessary for functions. But this is an equation. So that's kind of like also related, because you could say A equals 2 equals f of b. And then you could say f of b equals 2b, or 2 times b, however you want to represent it. I'm just going to say 2b. Or I'm going to put a space in there and then I'm going to draw it myself. Whoops. Because it's smaller than a regular x, and it's like a little bit higher up than a regular x. Is how I view it anyway. Sometimes people use multiplication symbol as this, the asterisk symbol. That's also okay. I don't know. It's just multiplication. There is addition, subtraction, multiplication, and division. Addition is like 1, 2, 3, 4. Subtraction is like 1, 2, 3, 4.
actually, I don't know how to say it. Like, you're adding them together, and then this is like, you're only including this. So this is being subtracted or something. Or, I don't know. You're like cutting out part of it. You're saying no, not to include this. Or you're saying like this minus this. Like this position, let's say this is position 10 and this is position 0. The distance from 10 minus 0, or let's say this is 5. The distance from 10 minus 5. Fuck, why isn't it letting me type 1? What the hell? Oh, numlock. 10 minus 5 equals 5. That's just how numbers work. That's just how subtraction works. That's just what subtraction is. There's also group theory. Group theory is really relevant to this. If you're interested at all in number theory, you should also check out group theory, because that's kind of like how these operators work, is group theory. And they can work differently. They actually can work differently. They work differently in some other systems. Multiplication is kind of cool because it's like a multiplication table, like 2, 3, 2, 3, oops, 2, 3, this is 4, this is 6, this is also 6, and this is 9. So what you're doing is you're multiplying the numbers here. And so when you multiply them, you get this result. But it's also, you can also think of it like 3 by 3 is visualized like this. There's 3 on this side and there's 3 on this side, and then you say 1 for this intersection, 1 for this intersection, 1 for that, and so on. And then over in this area, there's now 9 dots, or whatever they are. Squares, I guess, in this case. But they're, oh, did I not draw that one? But yeah, that's how you multiply. And then division would be like selecting, how would you do that actually though? Because you can divide like 2 over 3. That's a weird one. How would you visualize that? If you've got 2 by 3, so let's say, but that's not how it is though. That's not actually what's happening. What you're really doing is you've got 2 and you're trying to say, where are the 3s? Like, this is like this divided by, or yeah, it's like, it doesn't actually, you can't draw it, you know? You can't draw a fraction of a pixel. There's no fraction of a pixel. Because that's what a pixel is. It's the unit of the visual space that you're using, right? Unless you've got some weird other kind of display that uses like lights that are not like pixelated. But you can lights that are not pixelated is probably going to be like a graph, which we're going to get into soon, which is just like lines between boundaries. And it could be multiple lines. It could even be arrows. It's all sorts of shit. But then there's also other words for graph, like this is a graph, a function is a graph, x squared can make a graph. The graph is the visualization of it. The graph is the xy plane and the function plot showing you where the curve is that shows you everywhere the function is actually happening. Because when you input like an x variable, what it kind of does visually is it points up to where the curve is, and then it says this is the y variable. And that's really just because you're using the x as input. So let's call it a and b. I feel like I'm slow or wasting time, but this is a function. This is how a function works. So this is a squared equals b. This isn't a function. This is an equation, and it goes to vertical at the end. But oh yeah, the angle is related to the slope, but that's kind of like, I'll get into that. Brain matter. Don't forget to eat and drink and sleep lots. To do nothing sometimes. If you get anxious, I promise, doing nothing sometimes can really be nice. It could really help. Sometimes. Just like do nothing. Or consider contemplating your thoughts. But that depends what you're thinking. So fractions, it doesn't exactly work. I don't know why that's there. It doesn't exactly work because you're kind of like, you have to divide it into 3. So you're saying like 1/3 times 2 is equal to that, equal to 2/3. So you divide it into 3 and then it's 1 out of 3. There you go. But yeah, fractions are weird. So that's just those basic operations, but those are really like fundamental. There's also the percent sign, which is used for 2 different things. It's used for modulus or percentages. And they are related. I suppose they are related. I've never thought about how they're related, but they are related. But it kind of makes sense because this looks like a division symbol with circles. I don't know if I should explain this. 100% equals 1 out of 1. If you want to understand it, that's it. 50% equals 1 out of 2. 25% equals 1 out of 4. I think you get that, probably. But the 1, whatever, like the units, oh my goodness. I'll get into units. Space and time have units, but like I had said before, you're measuring them relative to something. So space is measured relative to some actual distance, and time is measured relative to something that's moving, and it has a velocity. So if you want to have definite perfect measures that are like invariant to anybody, that don't require you to like bring them the meter stick, then what you really want is something like the speed of light, because that's constant everywhere, at least as far as we can tell. But that's kind of really, really fucking fast. So I don't know how you even like use that in everyday life. It's the speed that things without rest mass go. So they're just like, the light wave has kinetic energy in the field's motion or something. And sound has kinetic energy, and it has potential energy too. I'm sure there's potential energy in electromagnetic waves. But energy is important. I'll get into that with physics. Modulus, that's often what we're talking about with percentages though, is percentages of energy or percentages of time or percentages of space. Most of the things that we talk about are space, time, or energy. And energy is either kinetic energy or potential energy. And kinetic energy is because of motion, and potential energy is because of distance and I don't know how you say it. Distance and I don't know. It's just whatever the field is, I guess. Distance and interaction. So that one's kind of more complicated. I can get into that. So I would say like this is what potential energy looks like, and motion looks like an arrow because it's moving in that direction. Whereas this has a lot of photons going back and forth between the electron and the proton, and that's how the potential energy forms, is because the photons keep going back and forth, and it transfers the information and the energy, and it generates this potential energy. But it's special because it has no mass, and physics is weird. So I'm not going to get into that too much. But when we're talking about percentages, they're very important because they're usually talking about energies being compared to one another with space and time. So you're comparing the distance between 2 energies, so the space between 2 energies, or the time between 2 energies, which is basically the same energy. Like I'm the same energy as I am right now to now, but some time passed between them. All right, let's move that away for now. Percentages, I explained. Modulus is a remainder. Modulus is remainder. So 5% 2 equals 1, because 5 divided by 2 equals 2.5, and 2.5 and 0.5 times 2 equals 1. So you take, this is the important part, is the fraction. And this. And 0.5 is the remainder, is the part of 2.5 less than 1. The after all the rest is counted together. So the 5, like it depends on how you count it, you know? That's what we're talking about. So really all of this is space-time counting. Space-time and energy counting. Everything is space-time energy counting. Everything. And we're gonna get to that more and more and more. But that kind of explains modulus. It's a remainder function, so or an operation. So this equals 1. Whatever you evaluate this with your computer, if you type this into C# or Python, this will be true. The equal sign will be true because of what this percent sign is doing, and because 5 and 2 are numbers and 1 is a number. But this thing is doing something. Let's get into functions now, because these are some common functions. Common functions that everybody uses all the time, every single day, every single second. These functions are being used. All of these functions are extremely important. Common number functions. These are related to numbers, which, like I said, there's continuous and discrete, and you can decide whether you're going to include 0 or not, and you can decide whether you're going to include negative numbers, because of course you can have positive 1 and negative 1. 0, 1, positive 1. Usually you just say 1 is positive 1. That's usually what people talk about when they say 1 is positive 1. But it depends on the context whether negative 1 even means anything. So, like, you can't say there's negative humans. There's no negative human. It's not like you have an inverse existence, a negative existence. You exist. You either exist or you don't. Like, an electron either exists or it doesn't. So there's no, like, negative electron. There's a positron, and they can annihilate in an anti-particle combination, but there's not as many positrons as there are electrons. Maybe that's true, though. Maybe there's, like, antiparticles for every particle. I'm not sure if that's true, though. There's, like, CPT symmetry in, like, advanced physics, charge parity time symmetry. So charge is like electrical charge, and then parity is like I'm not sure. It's either related to like chirality, like the direction of rotation, like spin, or it's related to some other like fundamental interaction. Either the strong force, weak force, gravity, or electromagnetism, which are all the fundamental interactions. The forces and interactions go together, all of them. All right, positive and negative numbers. You've heard of those. Obviously, you don't use them all the time. You don't use negative numbers all the time. So, this is kind of what you've heard of, probably, when you've heard of functions and things. Now I'm going to try to explain the logic. Let's also explain logic, because logic is also there. Logic is also important. Logic is like and or. This is a symbol used for the or operation. Let's label them and, or, not. Oh yeah, this is another exponential So like 2 to the power 3 equals 2 times 2 times 2. You've probably heard of that as well. And then 2 to the power 4 equals 2 times 2 times 2 times 2. And that's a little bit weird, but it is, sometimes in programming, they'll do like that, just as a different way to visualize it. I don't know why they don't use this, honestly. I guess they're all different symbols, you know? These are logical symbols. So all of these work on numbers. All of these work with numbers. All of these work with numbers. So if you're a programmer, you would know this. You would know that all of these symbols are used in at least English programming. We have an English keyboard, and probably a lot of others too, just because it's not even English necessarily, is it? I think they use these symbols in other languages too to describe operations. These are also symbols that are often used. Or is kind of a weird one because it's like this big vertical line. It's like L. This is an L. This is an OR, and this is a capital I. That's kind of weird. The L, yeah, it's the font is different too, so the way that the symbols are rendered is different. It's kind of annoying. And then there's obviously capital versus lowercase. Funny joke. Shift, or caps lock. So these are really important. So, and this is like fundamental logic. So I'll explain fundamental logic. So fundamental logic works with these Venn diagrams. So if you've got a NOT gate, that's different. These are Venn diagram ones. So that's that, and this is this. So this is like the two things that are being ANDed. So all of these symbols, you could put a symbol can do anything, you know? You could just make a symbol and you can say, oh, it does this. And then as long as you do the things when you see the symbol or when you are processing the symbol, when you've decided you want to process the symbol can like do the thing or it can remind you to do the thing. So that's kind of what these are with the computer, is they're hooked up in the computer to do what we want them to do. So this symbol will basically A and B. So there's A and there's B, and then this is the AND output. So you would put so this kind of like, this is what the computer is doing behind the scenes with the bits. So these have to be bits. These have to be, A has to be a bit, whether it's inside or outside of the circle. That's how Venn diagrams work, is it's either inside or it's outside. So let's say A is true, but B is not true in this case. So that would be like something being in here, but B, it's not in B, so it's somewhere out here. So it's somewhere out here. So it must be over here, but not. So the thing that we're evaluating, it's here, but it's not in here. So it's not true. It's kind of difficult to visualize it this way, but 1 is when it's inside, 0 is when it's outside. There you go. That's really what, or true and false. That's probably more accurate. So it's like a condition. It's a condition of whether the dot is inside of the boundary. And then a Venn diagram is basically saying if something is inside both of them, then it will output true. And this is kind of a crummy way to examine it, but I don't know if this is like a good way to visualize it with the boundaries. I'm just gonna say true and false, because that's what it's really doing. If you want to say that this is that this is true and this is false, like where does the dot go? I don't know. It's over here now. So, and then true and false is like words that mean something versus a thing being inside of something else, it has truth to it, but it's kind of like not a word. I guess the word is more helpful because it's specifically like, it's true. Like, if 2 equals 2, like, that's kind of what the equal sign is doing. I hate it. I honestly hate it that programming, they say like A equals 2B, but what's really happening is there's an arrow this way. 2B is being computed, 2 is being multiplied with B, they're going together, and then the result gets stored in A. But they're using the equal sign for it, but that's not equals, that's not equality. It becomes equal. That's what's happening, it becomes equal. But here, actual equal sign, like what the equal sign actually means, if you're not like a crazy programmer about it, is they're already equal. Like, it forces people to use like JavaScript shit where they're like, oh, it equals equals or equals 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 or whatever. And it's like, well, then they're like talking about objects inside of objects inside of objects, and you're saying, oh, you have to compare them, and how deep are you comparing the parts of them? It's like, use a function. You're not even checking if it's equal. You're not actually doing that. And then you use the equal sign. So I'm not going to use that when I make that a programming language, if I get around to it. So this is true. This is like an evaluation. That's kind of an important part to these things with computation and logic, is you are evaluating them. So your system of logic is constructed such that things can be equal to each other, things can be different from one another, and they can be compared. So true is like not equal to false. So if t, let's write the whole thing. And some programming languages, it's like, oh, you have to do lowercase or uppercase. It's like, it doesn't matter. It's the same word. But true is not equal to false. But the funny thing is, if you typed this is not usually how they say not equals, but this is how I prefer to say not equals. Usually they'll do like this. And I guess that's fine because it's using the not function. And, or, not, and, or, not. And then this is not equals. But this is also not equals. This is also not equals. But it's true that it's not equal. That's the thing. So this is a fundamental thing. If you accept what this means, if you accept that this set of symbols means not equals, then if you're a computer and you want to hook up the functions such to do what you want it to do, then what you're really evaluating is whether the two things on either side of here are the same, whether they're identical, whether everything about them 100% is identical. Like, these are 100% identical. If you were comparing 3x3 grids of pixels, these are 100% identical, and it would verify that for you, because in the code, in the arrays, it's literally like, this is the color, FFF, FFF, 6 Fs, or 6 zeros, or whatever fucking stupid color it is. And F is like, you know, look, see how they're using, where do I look? They use the, I can't really show it, you can see though. But it starts to use numbers at the lower numbers, but it's a different number system. Number systems, I'll explain that. So, bits, yes. True and false are, they correspond to bits, and you can call them bits, but they're not the only bit. There are many bits. So a bit is just anything with exactly 2 possible states. All right, this is a mess. We're gonna come back to it. I'm gonna, this is the order that I made them, so I'm gonna keep going. This is a long video. I'm sorry. I'm probably gonna stop after this, and then I'm gonna make a separate video for physics, and then I'll make a separate video for like more complicated. This is like compositions of things. This is pretty fundamental, but entropy is complicated. Entropy is weird. I'm going to explain entropy and time and what is it called? Ergodicity, which is like the tendency of things to return to the same state. And that's kind of like a consequence. That's like a inverse thing with entropy. Like entropy is the tendency of things to change, and that's why it's related or maybe identical to time. Actually, no, it's not identical to time. Time is the direction. Entropy has like quantity to it. It is the change, whereas time is the dimension through which the change occurs, I guess. It's kind of weird. I'm not describing it perfectly because entropy depends on how your coordinate system is set up. Then ergodicity is kind of like an inverse counterpart to entropy. So entropy is the tendency of things to change from where it is now, but ergodicity is the tendency for it to return to where it was in the past. So I'm sitting in my chair. There's ergodicity that tells me I'm probably going to sit in my chair again. I'm standing up. Now I'm sitting down again. So there was a statistical tendency for me to sit down in the same chair again. The chair didn't disappear. I didn't go somewhere else. You know, everything stays the same. But it's even more broad than that. It's like a universal theorem, which is basically also related to this idea of space being difference itself, which is the idea that the spatial configuration of particles or whatever the fuck it is in space is the state. That's the state. The spatial positions is the state. And that hurts my brain because I don't want to believe I'm just state. I'm also charge, I'm also spin, I'm also velocity. So there's all these other things that are not just position. But position is a way to visualize it maybe. And that's kind of why it is confusing, because it'll be like, it's not space, but we're representing it with space. So you see it as space, even though it's not. But all of it has to do with space. Because if you have space with no time, if you have time with no space, or neither, then nothing like can relate to anything else. Like the way that things can be related to each other is that they're in different positions. Like if everything was in the same position, so no space, to me, what that would mean is everything is in the same exact position. And what that would mean to me is that nothing can ever change because you're not calling the changes spatial, like even though they are spatial. Like a charge, you could call that a space actually, but it's a discrete space maybe, like plus or minus one, like an electron is plus one and a proton is minus one, or vice versa. They do the vice versa. The electron is negative, but it actually doesn't matter. You can do it either way. It works exactly the same. It works completely perfectly fine either way, whether you flip the signs of the charges. So when they say electrons are negative, it's a convention. All you really have to remember is that they're the opposite. But it does help to remember that electrons are negative, just because you know what they mean when they say it. There's a lot of things. If you want to be really smart, and intelligence is all about being really lazy but still distilling important information. That's my opinion. Is if you want just memorize stuff based on distillations. So what was the thing I was just saying that I wanted to distill? Fuck. Time and space. I forgot. Damn it. Yeah, intelligence is like just a word. Everything is just words that I'm making with sound with pressure waves. It's a weird shape. Ooh. Or it's a shape on the screen. Ooh. That's crazy. I never would have guessed that. That things could be present in space. So, let me show you the main course, because this is the part that's awesome. And it's related to this. So let's even show you this. So you can nest these three different types of things in different ways, right? So let's say uniqueness is extremely important to our understanding of a variable because we don't know what it is. I can't tell you for sure if charge is a space or not because it doesn't, like, is there a space there? Can it move along the space? No. But it is different and it does cause things. It causes things. There's all this weird shit. So you can't, not everything is just space and time. There's also substance. There's also like a thing that is relating to other things in a way that produces kinetic energy and potential energy. And the combination of those things is why it's energy in the first place. It's very complicated though. It's like, I don't think anybody has, some people recently have been talking about, I mean, it's quantum gravity. That's the main thing that everybody gets confused about. And that's the reason, partly, that's not the reason, that's a reason partly why I was interested in this stuff, is quantum gravity, because they contradict each other. In a black hole or in the Big Bang, there's contradictions between quantum mechanics and relativity, which is the modern theory of gravity and of near light speed travel. If you go really, really fast, time actually slows down because time and space are kind of like really fucking weird. But they're still there. It's still space-time. It's still space-time. But I think people underestimate that space is real by itself. I think people don't see this as much as I do, maybe. They don't see this. They don't see, like, this being here and this being here, but them being different. Like, if the most obvious thing when you look at this table, because this okay, I should have shown this to you. This is maybe what I was going to explain. I'm not sure. This is basically it though. Let's just do it right here. This is a boundary and this is a boundary. So you can kind of tell. Let's do it in a different color. It doesn't really matter. So this is time, and this is, or sorry, that was space, and this is time. Let's do different colors just so you can tell the difference. So this is time, and that's space. So, fuck. This no is me saying that that's not a possibility. That doesn't make any sense. But maybe this is why electrical charge is a thing, or some weird shit with like antiparticles going backwards in time. Maybe that's why they say that shit. I don't know. But that, like, how can it have no space? That I don't believe that. But that's understandable from my perspective because I'm like the space is emergent from the difference, if space is emergent from something, then what is it emergent from? It's just emergent from differences in space. So what does that mean? I don't know. But this circling, let's just visualize that really quick. So let me just show you the image because I have a thing for this. There's this, that's one thing that's really good. Then there's also this. This is what I was talking about. Stars. Pretty stars. Some of them are actual from the Hubble Deep Field, and some of them are just like sprites. Okay, so this is like basic logic. So true and false. So not, that has to do fundamentally with the idea of true and false. So not true equals false. Not false equals true. That's what true and false mean. That's what they are. That's how they're defined. That's what it means. But that's not the only part of their definition. True is true equals true. And true equals false. So the saying something, this is really related to this idea of difference and similarity and uniqueness and specificity and identity. I'm glad I'm keeping in the same video. This is all like non-physics. So I'm talking about space-time, but I'm not talking about our space-time necessarily. Not specifically our space-time. I'm talking about space-time in the most general possible conceptualization of possible space-times. And that's maybe a difference that makes it confusing, but it also makes it extremely general and powerful. But when I talk about, what was I talking about? Specificity and uniqueness, like, these are all true. All of these equal signs, when I evaluate them, I say they're true. That's how I define true and false, is true and false are defined with this. And maybe even equals too. Like, true, false, equals, and, well, you don't even need the parentheses. Well, you do need the parentheses because you need order of operations. So you would need to say, are defined. So these two things being equal, they're the same, but they're in different positions. So we say they're equal. Even though they're the same, but in different positions, we say they're equal. Are they exactly? Sometimes they're not specific. They're not accurate with equality. When they say it's equal, but it's not actually equal. Like 2 equals 2.1. 2 equals 2.01 or something, like a 1% error. And they would say, if you put it in parentheses, so you're counting the whole thing, equals true. The parentheses does order of operations. I'm going to get to that as well. That's an important. Let me show you the picture I have for that. Order of operations is. I don't want to have to draw the picture again. Oh yeah, this is kind of like. This is kind of something else, but this is like. Fuck. Yeah. So both is A and B, and then A and not B is this, and B and not A is that, and then neither is neither. And I spelled it wrong. Because, nah, I guess. What was I looking for? Compilation triangles. Where is it? Maybe it's white background? Is it a black background? Where is it? I pulled it from online because it's like this is just how compilers work. No, that's not it. Yeah, I guess it's not in this folder. I gotta go to my folder of other people's diagrams. Okay, it was in my folder of my favorite diagrams. Although I don't know if that's actually all of my favorite diagrams. I'm messy. I have too much stuff. This is kind of like a way to visualize order of operations is a compiler tree or a compilation tree. So it's compiling, I guess that's different from composing. I'm not sure exactly how. Composition or compile. So the pile is like, I don't know what the fuck I'm talking about. I'm just talking about words now. But this is how order of operations works. So this would be, I'm gonna move over to the other screen because wait, I can do this. View, topmost window. All right, so now this is wait. So you have to put it in parentheses. A times B plus B plus C minus D divided by 2. So this is the equation for this compiler tree. A times, and then the plus, if you ever do programming, functional programming, it uses a lot of parentheses because it wants you to be extremely clear about your order of operations, and it wants you to use extremely clear functions. But then they use like commas and other stuff, so it's a little different. But they're all fundamentally doing this at the basic level. This is fundamentally what the computer is doing when it compiles it. It's doing the order of operations, and it's doing the functions that are defined in the order of operations. So when I say evaluating, I'm saying you do the operation. So multiplication, you can do that operation with the computer. And it's a little more complicated with these multiplication and division, and like it depends on what the size of the number is, like how you're inscribing it into the machine. Like what are the bits, like what are the zeros and ones in the variables, how are they described. That is relevant to how you're going to do the operation of plus, minus, subtraction, so on. Plus, minus, multiplication, division. There's different words for the same thing. Subtraction and difference is related to subtraction, but it's not subtraction. You can make a subtraction based on a difference, but the difference might not be covered or fully described. Like there might be something else to that difference than just the spatial difference or the subtraction of some whatever quantities are different. Like me minus you, is that defined? I don't think so. I don't think a third party can take a human being and say Luna minus Joe. You can't, I don't think that works. That doesn't make any sense. There's no like operation defined for that. Whereas a number it can be described in bits, or it could be described in like how many fists am I holding up, and that's a number. The number is related to something. Let me talk about number systems, and then I'll talk about this with my function system, because that's the fun part. That's what I'm looking forward to. But I also want to talk about everything else, so it's a kind of a long video where I'm going to talk about everything. Be my crazy self, and I'm going to finally... Yeah, it was face reveal. Hi! Crazy. Well, okay, I already forgot. I'm going to figure it out. I don't know what that is. Numbers, operations. I'm going to get to this, but first... Number systems. So this is a really important thing. If you want to know how to program a computer, you have to know how binary works, or else you're going to fail really quickly. Because binary is how this works. Binary is what this is doing right here. This is binary. That's what is happening here. That's why these are the same. These are the same, even though they're in different positions. I'm going to draw this better now. Can I like file... I don't know if I can open this with can I copy the image? Copy to clipboard. Will this let me? I don't want to have to open it. Yeah. Okay. So this is like, let's say AB. So we're gonna have. I'm gonna make. No, these are bits though. So it's a little bit weird. Oh my goodness. Oh my god. All right. Like the bits are pretty clear. Well, it was number systems. All right. So there's number systems and then there's variables. That's the two things I'm gonna go to. So there's number systems and then there's variables. So this is like two things, and then this is one, and then this is 0, because it's not a. So if 0 is a not, if you have to define it that way, you have to agree and use it that way. If you use it that way consistently, then the definition works. That's what a definition is doing here. By saying 0 is a not a, you can use as false. So 0 is not always false, right? It could be a number, or it could be, like, it depends on where you're putting it, and I'll get into this. I'll just draw it really quick, because it's 0, 1, 2, 0, 1, and then you can do this. These are my variables. It's really pathetic. Somebody's gonna steal this, and they're not gonna give me credit, and then I'm gonna be sad. And that's like a function as an arrow between or something. Or maybe it's like a possible function, and that's like God. That's like you making free will decision choices is possible functions. Because you can decide which function you're using. Although you're made of stuff, so good luck. Okay, But this does line up, like I said. 0 or underscore 0. So the underscore is kind of like the variable. The underscore here is like uncertainty. Like I don't know which one it is. But I'm just kind of trying to explain how this here relates to this A and B thing. Because this is a really fundamental, whoops, what was that? Did I just like, where did that even come from? I remember that, but I don't remember, how did that even, that was weird. That was like all the letters combined in a table like this. I'll get to that though. You could do letters instead of numbers here. And then you can 0, 1, 2, 0, 1, 2, and then you can have like whatever the fuck you want to put there, you know? You could put anything here. And you could put anything over here. All of these are x's. Everything is x. No, that's not true. Everything is a variable, and x is a common variable that most people know about, but it's also just a symbol. A symbol is a shape. Yeah. And the shape definition, if you want to use it the same way over and over, you could say like this is an equal sign, and this is an equal sign, and this is an equal sign, and this is an equal sign. But how do you decide which one is like a valid equal sign? And then it gets into like fonts. How many fonts are there? A lot. Too many. At least there's Aleph. I like this one. It's cool. It looks old, but also like based. I don't know. Okay. Did I explain this? I'm going to explain number systems now, because that's important to how computers work. I need a whole nother image to explain number systems. This is a really common thing that you learn when you first get into computer science. So let's go. 0, 0. I'm using Aleph because that's what I had. 0, 0. Then this is 0, 1. Then this is 1, 0. And the order matters over here. That's why we're doing it in this order. So this, we're saying binary. So this is binary. Number correspondence. So it's a binary number or it's a decimal. So they're equal. They're all equal. That's what we're using. This is 0, this is 1, this is 2, and this is 3. And then if you want to keep going, you can say 1, 0, 0 equals 4. And so the way that that works is basically each number place, the positions of the numbers tells you how big they are. So if it's in another place, you're multiplying by the base. So like I said about this, where did I put floating point number explanation? Here, 10, decimal. You see how it moves the decimal place over? So it moves the decimal place over with arrow, kind of. It moved the decimal place over here instead of here. So that's kind of the same thing that's happening with this, is you're just moving it to the left and putting zeros on the right side of it. Let's make even more examples. Most people have some kind of knowledge of this, and I don't expect you to memorize all of them, but it's good to know how it works, because this is really fundamental to how computers work. Let's say this is that, and then this is even that. So this is 8, and then this is 16. So every time you move the point, there's a decimal, or a whatever you want to call it, the end of it, the part where it reaches 0, like actual 0. You know, because zeros, you could put as many zeros as you want, and you can put as many zeros as you want to the right of the dot, or you call it decimal point. That's the reason why I'm confused. But you could do it with binary. You could have 0, 1, 0, 1, 1. You could have that after a decimal point, But then would you call it a decimal point? I don't think so. Maybe it's like a, I don't know what it's called. A binary point. It's not a period though. It's not in like grammar like English. So it's not like a period, I don't think. I don't know. But each time you move it over, you're basically multiplying or dividing by 2 because we're in binary. But in decimal, if you say 100, this is equal to 10, or sorry, let's do 20 equals 2 times 10, because we moved the decimal point 1 to the right. So it's the 2 times 10. So every time you move the decimal point, because decimal is when you have base 10, if that wasn't clear already, I'm sorry. That's base 10. So these are 10 to the power of x, or 10 to the power of e, a times 10 to the power of e, and this is a times 2 to the power of e. And that's kind of like how you have to do it. And then a, or -1 is less than a is less than 2. Or like a equals 0 or 1. A I don't have the symbol for it. But basically a is from 0 to 10, or sorry, to 9. You could also start doing this though. If you're gonna do scientific notation, which is totally fine. Like I said, you could even have scientific notation with binary. The scientific notation is when you do this, when you have the exponential actually shown. You actually show the exponential. Binary is all these, and decimal is all these. So these are all decimal, showing an equation in decimal. And this is kind of like telling you like the numbers have to be within this. Wait, is this true? Yeah, this. But that's the thing, is you can put stuff after the dot, so it's kind of like this isn't accurate. But the symbols used in binary are either 0 or 1, and the symbols used in decimal are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. You always use 0 in every single base. That binary is the smallest base. You can't have a base 1 number system unless you're using tallies. And then how do you count 0? 0 is just this. 0 is nothing. There's nothing there. That's 0. That's how you do a tally of 0. You can't do a tally of 0. And it's a waste of space too, because of the way the computer circuits work. Is you have a state, so it's either here or it's here. It's either here or it's here. Maybe this is 0 and this is 1. This is 0 and this is 1. Is the state of like a switch in the computer circuitry. And so it has to be like one or the other. I don't know what I'm saying now. Okay. I'm tired now, but this is getting to the good part, and then I can stop and I can make a different video about these other things. This is almost done. So, logic, all of this, and, or, not, that's all logic. Not is basically like false as opposed to true, or true as opposed to false. So like true equals false equals false. I wonder like what it would be if you like if you say true equals false. There are multiple ways to do that. I'm just gonna do that really quick, just to not leave you in the unknown with that, because it's a little kind of strange problem. True equals false. So if you said this, you wouldn't know the order of operations. You wouldn't know, oh, that's how that happened. That's a good image. Where was this thing? Compiler syntax tree. Is that even here? I don't know what images that was looking through to show that. That was weird. But this is a compiler tree. So it tells you the order of operations that it's going in. It has to be this, whereas this doesn't tell you the compiler like order of operations, like what order it's going to do the operations in, and that can cause issues with non-commutative operations. So commutative operations, it doesn't matter what order you put the inputs. I should have said that earlier. That's a really fundamental thing. Inputs and outputs. A function has inputs and outputs. So B is the input, and then this is output. But then the equal sign, this is like, this has an arrow on it. That's more accurate. How would you do this? So this could be true equals, I'm just trying to, maybe I'll figure out if this is commutative just by testing it. I don't have to look it up because I can test it. I promise you, a lot of the time, there's a lot of things that you can figure out, and it's more intuitive, and you'll grasp it better if you figure it out yourself. But sometimes you can't. Sometimes you just have to, like, you're missing key information or something. So it's not bad to look stuff up. This would be true equals true. See, this is the thing about the parentheses, is you evaluate what's inside of them first. And that's kind of how you know, is you evaluate what's inside of them first. So this would be false equals false. And then, so then once it's a single thing inside of the parentheses rather than an expression, that's what it's called when you have operators or operations or functions. So if you have a function with parentheses operating on that, this is kind of a particular way of, parentheses can be used for order of operations, but it can also be used to like enclose where the function is applying. So f is like a variable, but it's also a function. So that's kind of like you have to use it differently. And functions and variables are different, but a function is a type of variable, but a variable is like more generic than a function. So a function is a subtype of variables because you can describe it in bits. You can describe the function in bits. You can make a truth table with the function of the function. That's like what, that's kind of what this is doing. With the not operator, that's what this is doing, not. I'll show you the truth tables though with this. But this is kind of funny. This evaluates to true, and this evaluates to true. So the order apparently didn't matter. It came out to the same result both ways. I don't know if that's always going to be the case, but that's interesting. Maybe that's always, maybe you don't need it for that. But that's just equal sign. Most likely, most things are not commutative. Maybe equal sign is commutative just because of how it's like set up, I guess. Just because it's like, it is what it is. Or it's not. Either it is or it's not. That's the funny thing though about this equal sign. I feel like I got this intuition when I first started playing with my TI-84 calculator, but it's really important because true and false are not just like some weird thing. They are also variables. So let's get to that. So let's say I'm gonna do pretty symbols because I want it to look good. So I'm going to show 3 different types of variables. So this is the intuition I want you to get from this, is basically there's 2 different things, like this is an important, this shows you how they can nest. It's nesting, or containing, whatever word you want to use. Contains, includes. This is a relation between things that are included, which I might do just to show you like the order. Like you could draw a line between these, and now they have an order. The order would be the same no matter what, just because it's only 2. But you could do something weird like this. You could put these ones over here, or you could do like these ones over here, and then this is like over here, and that would be weird That would fucking confuse you, right? Because then this is like, if you're like going around the edge, it would go like this. That would be weird. It would go do, do, do. Which is weird. It's like, why aren't you going, why isn't it like this? You know? Why doesn't it go like this? If you're like a racer on the edge of it, and you're like going around, rotating or whatever, kind of looks like a football almost. Football head, potato head. Then which ones will you relate to within the boundary? So let's make these. So I don't have to do that. The order, I think, has something to do with how these are being described with all this stuff that I wrote down. Some of this is a little bit not exactly logic, but most of it is kind of like geometric and therefore logical. I am out of water. Out of. I hate that word, phrase, but it's true. Out of. So let's say this is true, and this is false, and this is 0, sorry, this is 0, and this is 1, and this is 0, and this is 1, and this is 2. So this is a bit. These are both bits. Bit and bool. This is both a bit and a bool. This is a bit and number. Trit and number. So a trit is basically just a bit with, I don't know what I'm gonna call these like variable things, because I had a different name, nits and nights, but I don't think I like them, and I'm changing how they work anyway, so it's kind of weird. But this is the thing you have to understand. When I put these true and false, this is the reason why it has to be the way it is. There's no other way for me to do it. Because the lines can either have gaps in them or they cannot have gaps in them. So that's why these two are there. But then this, what the fuck is this? This is the uniqueness. But its uniqueness is everything. Everything is unique. And so this can be anything. That's what I said here. This can be anything. It can be anything. And if it can be anything, it can be true, it can be false, it can be 0, it can be 1, it can be 2, it could be anything. And what you're really saying is that this has some function to convert it into 1, and this has some function to convert it into 0, and then you render it and you see, oh, it's a 0, oh, it's a 1, and you use your pixel brain or your vector graphics brain or your geometry brain to visually correspond that number geometry to the idea of 1 or the idea of 0. But this function has to occur in the computer. I don't even know like what the bit is. Like it's either a 0 or a 1, but it's not really a 0 or 1. It's really a state that's either one thing or another. And then, so what you really have is this this unlabeled uniqueness, and then it can go and become either of these things, or it could be one of those other things. I don't know where I'm like crossing these boundaries, but I don't know where the boundaries are supposed to be crossed for this, because it's not really a real thing. It depends on how you're using it. But conceptually, like abstractly is how I'm thinking of it. Like these are similar because they have the same exact shape other than what's inside and the curves of the boundaries, which is something I kind of leave out and let be symmetric. But it's a bit. It's still a bit. This is a bit. So in the computer, there's something, it's either this or it's this, right? So when I say, it's like, this is just a variable, right? Like, this variable isn't actually instantiated. So it's a variable, this is kind of like a shorthand. It's meant to give you the intuition of it, but it is roughly accurate, I think. Because this is merely a possibility that is bounded,
So it can be either the 0 or the 1, and it can have multiple, you could have multiple gapped boundaries inside of the solid boundary, and that's like the multiple possibilities. So these are each a possibility. So it's a possibility inside of a boundary. But it's multiple possibilities inside of a boundary. So that's kind of the weird thing is if you just have like this, sorry, doesn't line up exact. It's never gonna be perfect. If you just have this, even if you put like something in there, even if you put like 5 in there, like, I don't know what this means, honestly. It's like, it's only possibly 5. Maybe there's like something over here that it wasn't rendered, you know? Maybe there's a 4. I don't know, maybe they missed it. However they drew it is kind of up to them. But maybe this is a variable that doesn't have any possible states other than 5. So it's like a constant. It's like, this is always 5. This is just the data of 5. But it's like, I don't know. I don't know what the point of the gaps line is then, other than to say like, you're not using it. So maybe at that point, when you have something like this, the 5 is like just there available to you. Like it loses the meaning that is in this because there's only one possibility. I'm not sure how you would use it, honestly. And using it is kind of the thing that you want to do. You want to put it into a function. You want to use it as a function or use it in a function as input. So everything is either the input or the function. Function or input. That's what these things are. This is the function f, b is the input, and a is the output. And this symbol representation, if you go into the computer, b is really like, I don't know, some binary number. But then they have some binary code in front of the data that tells it what kind of data it is. So in front of the data, it'll say like, this is a number, or this is a XYZ. And I think in my programming language, I'd like to make it more clear, like, you define the types yourself. All of the types, you define yourself. The only thing that it provides you is the mechanism to define the variables, which would include functions. And functions are kind of like composed of variables, because what you're really doing with a NOT gate is you're taking this possibility space and you're taking it as a domain, which is a space of possible inputs. So they're possible inputs. They're not actual inputs yet, they're possible inputs. So if you had an actual input, you would have to do some kind of way, you'd have to represent it somehow. And I'm gonna say you would outline it. You would say, this is now false. You have to describe it somehow. You have to represent it somehow to your eyes or ears or some other sense, so that you know that it's true. It's truly false. It's true that this variable, let's say that this is like A, this is the name, I don't even know how to like say it, like how do you like assign a name to the variable? Maybe this is how, I don't know. Or maybe that's just something that's related. Maybe you just put it there not underlined and you like draw a line to it. I'm not sure. Because you're not calling this the name of it. Whatever. But outlining it solidly, right? These are the two outline types, right? You can either outline it solidly or with a dash line or gaps line. Could be dash or dots or whatever. Could be like triangles in a line, you know? Could be really big and it's got triangles. So this is your gaps line. That's their stylized gap line. It's still there. It's still got gaps in it. All of those are just gaps in stuff. That's how you kill the gaps, is you just say it's possible or something. I don't know. I just made that up. All right, I'm getting tired. Continuous calculus and discrete graphs, functions in logic and computation. Let's These are data types. Let's make some more space. So here's a function. This is a NOT gate. I have a page in my notebook of this, but this is a NOT gate. True. Well, the page isn't exactly this. False. So the NOT gate operates on variables. It doesn't operate, well, it operates on instances when they're instantiated. Fuck, this is actually not what I want to use now. Okay, yeah, this was wrong. I'm sorry, the key was all wrong. I'm just kidding, it's not wrong. This is a perfectly valid way to say it, because you could just say it's like possible, but there's nothing inside of it. Whereas this is like, there is something there, so it's definitely there. That's what I was saying, like, if you have like this, what the fuck is, or if you have like 5, or like this, 5, like, what is that? It's just a thing, it's just there. But when you add the dashed line around it, does that make it merely a possibility? Like, is this merely a possible 0, and this is a possible 1? I guess so. So then, but then why does the outline do anything different, you know? I think it's the immediate nesting, like the thing that's most directly outside of it. So if you put the outline here, this would be merely a variable that can hold 5. So if you wanted to describe it in the computer, you'd still have to say 5, but you'd also say there's no difference anyway between the different instances of it, so it's just 5. It's just the pixels that are in here. It's just what it is. That's the thing. It's kind of like a pain in the ass. Like, it doesn't mean anything unless you've got a bit. If you don't have a bit, if you don't have difference, this is really, you need the asymmetry. You need some, it requires some asymmetry in order to have like any actual variable. That's what variance is, or variability is difference. So the variability is between the 0 and the 1. It's the difference between them. It's the difference. So maybe there's like some other relations that you can put between the different things. Like this is like greater than or something, you know? Like how do you draw that, right? Maybe you draw a line and then you say 1 is greater than 0 or something. Or 2 is greater than 1. You know, there's like a greater than relation, or vice versa. 1 is less than 2. Same thing. Greater than, less than, it's the same thing. It's just different order. Okay. Don't want to waste any more of your time. So if this is a variable, and like I said, it's kind of like, what do you do here when it's just 1? But if you have 2, if you have a bit, then you can have difference, and then you can say, well, it's only one thing at a time, but it's still other things are possible. And maybe you have to like relate it to the boundary. Maybe that would be more clear to relate it to the boundary, and that would be like, that would help you understand. So this key is like not what I'm using anymore, even though it works fine for what it is, just to help you understand that instances have something. You know, like this true is still here. It's true that this true is still here. This 0 is still here. That's the thing about data types, is you've got like this data type somewhere else. Maybe it's like a 0 and a 1, and the 0 corresponds to true. Because 0 and 1, this is like how it's like native to the machine, and then this is like said to be true, and this is said to be false. Or this is said to be true, and this is said to be false. And yeah. But this is like the map that tells you 0 is mapped to false and 1 is mapped to true. So when the computer sees the 0 in the system, in the actual memory, because all the memory is in 0s and 1s, that's machine language, is 0s and 1s, it has to turn into false at some point. So there has to be like a mapping somewhere that says this is false, 0 is false.
But then you can also say like, well, which data type are you using? Are you using I don't know. Is it a Boolean? Is it a true false? Where did I put that? Is it a Boolean? Or is it a number? What is it? Right? A Boolean is not a number. False is not 0. False is not 0. This is not equal. This is like a mapping symbol or a function symbol or operation symbol. Like the computer has to do this in the background in order for you to have false or true in the first place be available. In order to have false or true appear, you have to have like the letters F and A and L and S defined, and then you have to have a string rendering engine that renders all those pixels with fonts, and you have to render the fonts with Aleph, and you have to have a font size and all this other shit. Whereas 0 and 1, that's like primordial, like you're using the number as the bit. And that's why it works so generally, or well, it doesn't have to be that so generally. It could work generally either way. You could do with A and B or true and false completely generally, but 0 and 1 is like simpler. It's smaller. It requires less symbols. There's only one symbol. You could say you could easily replace it with F and T. F and T or F and T, and that would be the same. But then it's going to be a little confusing, so you want the whole word, because you don't know what letters mean. What do they mean? What are they defined as? Definition itself is part of the process, so pay attention, I guess, to how it works. Go code. Go make a Python program. I'll make a programming language at some point, but I'm fucking poor, and it fucking sucks, and I'm going crazy because of it. Because nobody fucking pays attention. Nobody pays attention. Nobody pays attention. All of this is still good. All of this is still helpful. This is a cool thing. All of these things are cool. All these things are good. This is good. This is good. This is fine. All of this stuff is helpful. Let's talk about how you make a function with a truth table. So this was like its own thing. You can keep nesting like this, you know, you could just keep doing that. I don't know what that does. That's gonna cause problems. But let's make variables, because that's the most important thing. That's what I want to do with this. So we'll say 0, 1. This is not going to work. I have to make a bigger canvas. Oops. Okay. So, damn it. There's a few different ways you can do this. Let me see if I can find it in my book, in my notebook. There's like 3 different, oh yeah. Okay. Let's see if I can. You can't really see it, can you? What is this stuff on the right? I don't know. But you can see the stuff on the right too. But this is the stuff that I'm going to be doing from my book. So, there's 3 different table forms that I found. Maybe there's more that I didn't find. Unknown. Let's do it quick. So there's truth table, F1, F2, let's say 0. I'm gonna use 0 and 1 for everything here, because that's easier. No, just kidding. But these are supposed to be like particularities. I don't know. Let's just say A and B. So F is always a function. I never use F as a variable, at least. I mean, functions are variables. Functions have to be defined, you know? Everything is a variable. Everything is changeable. And this is how you're going to change a function, because this is how you make a truth table. And truth tables are how you define things extremely clearly. So this would make, this is like a NOT gate. This one's a NOT gate because it flips them. And this is like a just identity gate. So each function is like a gate. A gate is like a unit of functions that's used in circuits, but you could abstract it and say it's a function or an operation or a transformation or any of these fucking words that people love to overuse and overcomplicate. I love all the overcomplicated bullshit that's completely unimportant and not required to do the job of what you're doing, because it's just like magic, but it's also fucking annoying sometimes. But this is the idea, is this truth table has like an arrow to it. This goes here and it also goes here. So these are the inputs, or the single input, and there's each of these is a possibility. So if you get this input, then you definitely get these outputs. So you're choosing a function, so you could just as easily like get rid of this, and then it's just gonna work anyway. But you can have multiple functions in this type of table, in this type of table. So it's pretty nice. I'm gonna try and look at the camera more. I'm crazy, but I'm not crazy. You know that I'm not crazy. You know that I'm not crazy. You know. I know that you know. Even though I act a little crazy sometimes, you know. This is the fun thing, though, is that the tables can just have directions. So there's also this kind of table. So there's A, B, A, B. So you could say, and let's just like put this here just to fuck with you and make you see it the way I see it. So this is the input variable. Now these, so you can see the arrow, this is really important, the arrow up here, this is a really helpful position to put things in a table. If you ever want to like make it clear what you're doing, I would recommend putting an arrow like this if there is some kind of direction to the table. If you ever make any kind of table whatsoever, it's really helpful to do that. I'm talking about logic, functions, and computations right now, but everything is a graph and everything has calculus to it, so we'll get to that. So this is also a variable, so I'm going to enclose it, and then we're going to say this is also a separation that is being made, or this is like a separation of possibilities or something. I don't know how you do it. Normally you put like just a line like that, but it doesn't like go all the way over. I only cover this up on the left to make it an enclosed boundary so that you can understand like it's either A or B. Like A and B are like 0 and 1. Like you could have, you know, there could be a related A, B variable representation that you're using for things. This is your bit now. It's A or B. It's not 0 or 1. It's not true or false. It's A or B. So now you're at Bab or and then you can pronounce it differently. Okay. Now, what you would put here is some f of A, comma A, or f of A, A. Yeah, it's really a comma, because what you're doing is you're taking both of them as input. So both of these are variables with possible states, and then this is the variable that is a production of the A input and the A input. So this is a symmetric function. It doesn't have to be, though. Let's do a different thing. Let's do 0 and 1 to make it patently obvious that the shape is not the symmetry of... The shape of this table is not the symmetry of these being the same variable. Like when I say same variable, I mean like that, like a 0 or 1 bit. If you know what 0 and 1 are, or if you know what true and false are, then it's the same everywhere in the universe. So 0 and 1 and true or false, they are different things, a bit and a bool, like this is different from this, or sorry, fuck. I want to get rid of the solid outline now because it's not what it is. False. This is not this, but they're both bits because they have two possible states. That's what a state is the particular presence within a set of possible states. Everything is a state. Everything has a state. The state is just what it is. It's the uniqueness of it. But, yeah. There's a lot of different words, and sometimes I get mixed up because they're very slightly different, and you have to understand how to use them in different contexts. You go into the context, and you're like, oh, I have to use it differently here. And then you go out of the context, and you're like, oh, I don't know what to do now. You have to navigate it, you know? So this would be like A0, or the order could be whatever you want it to be, you know? Or it could be 0A. And this is A1 or 1A. And the or, actually this is like a bad way to say it. Like, I'll just say F, A, comma, 0. So I'm putting this one as first and this one as second, just because I want to, because you have to pick one. So maybe like this is like the first one or something. You could represent it with a line as the first one. Like this is where you start, is the line. Or like a filled in, anything, you know? You could just make some kind of asymmetry with the arrow that you put there, and that would help you understand the arrow that's being the direction, the order of the inputs. Because when it goes into the function, it's going to forget which one is which. It only uses the order to remember which one it's using for whatever the fuck it's doing inside of it. But if you make a truth table like this, then the inside of it is just the truth table. It's just following the truth table, you know? So, not input, and then not input, false, true. And then this would be true, and this would be false. And that would go this way. I don't know how to draw that. Like, you could just draw that, like. But this is a particular function of the input. You could also have, fuck, I want to get rid of this now. You can also have another function like this, which is just input, and it just copies the input. It just has the input exactly. And that gets into another thing that I have a diagram for that's kind of cool. Diagrams, where is it? This uses the instruction pointer, but it also uses the difference between copy and function. So function is basically the arrow is causing a change because there's an F there. So it's going through a truth table that actually causes change. So this is not this. Whereas a copy would basically be like input of input, or equals of input, or copy of input, you know? Like the function name is copy because it's identity. Like you would call it something that lets you know that the function is just copying it. False goes to false, and true goes to true, and 0 would go to 1, and 1 would go to 1, and 2 would go to 2. So a copy would include every single piece of information, that is stored in it, and the memory is where those bits and all that information is stored. The memory is that big giant grid of data that it uses for stuff. But it's also, if it's just pure data, if it's just zeros and ones, it doesn't know how to do that. The arrows have to have some meaning. It has to have a gate. It has to have some function defined. It has to have at least a NAND gate or a NOR gate, because that's what's required for functional completeness. And if you play Minecraft and you want to like build complicated things in Minecraft, you have to use that NAND gate or NOR gate. The redstone torch is a NOR gate, and you have to use that in order to make any other gate. because it doesn't give you the NAND gate, it only gives you the NOR gate. But you can use either one for functional completeness. And functional completeness is the concept of being able to make any function of multiple bits. So maybe you've got like 0, 0, 0, 1, 1, 0, 1, 1, and you've got like maybe some weird shit that it's doing, or maybe it's got like a many to one part of the function, and it's got like, I don't know, some weird fucking shapes. If you define the type and you have the inputs defined, you can have an output. And that's just metaphysics. That's just fundamentally everything. That's just how anything works at all. Is if you define the type and it has a certain number of possibilities, you can make a function that outputs that type or uses that type as input. So that's what I'm going to do in my programming language once I have the fucking symbols in a line in a string. All right. This, you could probably figure this out, but it keeps going, of course. This is f of a1. I feel like I've said a lot, but I feel like I've also said a lot of stuff that I don't think I want to be lost, and I think I've said a lot of things that are like complicated, so I'm gonna keep posting this, I'm gonna keep recording this, I'm gonna post this on my new YouTube channel. Hi. Hello. Hi. Am I gross? I'm sorry. I hope that close-up wasn't gross. Okay, that's not what's important here. What's important here is math and science and utter amoral cruelty of math and science, because truth is true no matter whether it's good or not. It's true that innocent people and children are being bombed and killed in Israel and in Palestine right now, and that shouldn't happen. We should just not be killing anybody. But then people want land, and it's like, fuck you. Who's the state? Who's the government? And when I say state, I don't mean exactly like this, although everything is this, 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 anything is everything. But that's like the monopoly on power. But it's true regardless of whether or not it's moral. So when I talk about all these things, it's amoral. I know this is kind of weird to bring up, but there's moral, there's immoral, and there's amoral. And a lot of people like to say you're immoral even though you're amoral because they believe that their morality is right and your morality is wrong, or their morality is good and your morality is bad or evil. And so they're like, well, you're immoral because you're outside of my moral. But really, amoral is just everything. It's amogus. But everybody prefers different things, and that's kind of the basis of morality, is preference, I think, and health, I guess, of life. Life is pretty important to ethics, life and preferences, because you can't really make choices if you're dead if you don't exist, right? Yeah. Sorry, that's bad. I shouldn't do that. Don't do that. It's got safety on. Okay. One more table. This is no, I don't know. I forget what this one is. This one goes this way. So it's kind of cool. This one is pretty powerful. So this one, let's get rid of this because this is I'm going to describe these two. I'll post a picture. I'm explaining these though. But I'm explaining them again in my own way. And maybe I'll save these diagrams even though they're really fucking messy and you can't understand them without my explanation. I'm sorry. This is how I work. And nobody talks to me, so I hope it helps. I hope it's broad and yet also distilled enough. Even though it's a mess, I think it's still helpful. I'm gonna do it anyway. Okay. I don't know what that was. Okay. Help. I think it will help you reach your preferences. I think you egoistically will benefit from the things that I'm saying. And I think you will egoistically benefit from understanding the difference between you and others who say they own everything, or that you're bad or evil just because you exist, or that you want to exist in a slightly different way, or just a different way, I want my hair to look different. Why can't I do that? That's my preference. It's not like it's dangerous or something, Anyways, and it's dangerous is like risk, I guess. And then risk has to do with aim, and then it's like, oh my god, I'll talk about it later. Maybe I'll talk about risk. Risk is like, oh my god, I'm gonna have to like fucking talk to investors and tell them that they're all assholes. But that's okay because money moves things. Okay. This one's kind of funny because it shows the outputs as possibilities too, which is like this if you did this, or if you like if you did like this. This is an equivalent way to view a truth table. I just thought of this, but it's also, I just thought of this being exactly correspondent. Correspondence is kind of like a symmetry, and symmetries are not mutually exclusive with asymmetry. Mutual exclusivity means that they're like this. There's no intersection, but they're not mutually exclusive. Asymmetry and symmetry, they have stuff in common. You can have stuff in between. Everything is like that, really. Everything is different, but also the same. Unless it's like particles that are in exactly the same position and they're exactly the same particle. But that's like quantum mechanics, and that's like, fuck. But most things are like what I said, you know, normal. They can't be exactly the same. Most things are the intersection of symmetry and asymmetry. They're similar, but they also have difference. They have certain, symmetry is just saying that there's something that's the same. Like the two, is that the back side of the moon? I think so. People like to say the dark side of the moon, but there's no dark side of the moon. There's only a back side of the moon because the moon is tidally locked. So here's the Earth. This is the moon. Maybe the moon, this is like the lit part of the moon. My name's Luna, I love the moon. The moon is so cool. The moon is how I learned orbital mechanics, plus the sun and the earth. No, I'm just kidding, that's not how. I learned with F equals GMM over R squared. That's the equation for Newtonian gravity. I'll get to that. Newtonian physics. But it's so cool because you can do this every time step, because F equals ma, force equals mass times acceleration, and A equals dx over dt. Sorry, no, dv over dt. So this is velocity. Acceleration is change in velocity or change in time. And then velocity, v equals dx over dt. So velocity is change in position. Acceleration is change in velocity, like a rate of change. That's what calculus is related into that, I guess. Maybe I'll leave the calculus for physics, because that's kind of like a pain in the ass. I can talk about graphs, though. Graphs are cool. Calculus, you have to get into this like infinite sum of like tiny differences, which you could call them deltas because they're differences, or you could call them epsilons if they're used in a certain way, because epsilon is like an error. Okay. The moon, it has a back face, and that's this face, the one that doesn't show. So this is the back face, this one over here. And you can see it, there's a map of it, because they sent satellites around the Earth, or rockets that orbited like a satellite around the moon. They probably have satellites around the moon still, to a certain distance, because once you reach a certain distance, there's like a boundary of where the orbits are stable compared to the force of gravity from the moon and the force of gravity from the Earth. At some point, the forces make it kind of unbalanced, and there's like all this complicated stuff like Lagrangian points. Is that what it's called? No. Something like that. Some point where it's like pseudo-stable. Oh my god, I have to get into chaos theory too. Fuck. I have to put that somewhere. God damn it. I want to talk about that now. Fuck. No, I'll talk about it with entropy. That's like this. And chaos. I should have done commas. That's okay. The back side of the moon is different from the front side of the moon. But both both sides have things in common. They're both made of electrons, protons, and neutrons. And the electrons, protons, and neutrons are the same, but they have different position. So they're similar in the ways that they're the same. So similarity is like a subset of possible information about something that is the same. So if this is similar to this, if my left hand is similar to my right hand, it's because there is a sameness of the things that can be told about them. Intelligence. You tell something about it based on senses, based on inputs, based on inputs to a function. Like equal sign is actually a function that evaluates true or false based on whether the things that are inputted to it, A equals B, it evaluates true if A is equal to B. Now let's mix them up. But that's true. That's what equality is. If they're equal, that's what the symbol has to do with the word equal. You could say they're different. You could use it for chemical bonds. This is a certain type of chemical bond, but then I don't know what you're doing because I don't know chemistry as well. I'll talk about chemistry though, because I know like very basic chemistry. Let's finish these tables, and then we're almost done. We're in the home stretch. We're coming down from it. We're gonna figure it out. I'm gonna explain how this relates to what I've just done, and then I'm gonna explain graphs, and it's gonna be awesome. A, B. So, A, look at this. So this lets you show multiple functions, but this lets you show a single function with the arrows. So I guess it doesn't matter, like it probably does matter like where it points, like if it touches the boundary or not. I would make it like exactly touch the boundary, and that would be like the most unambiguous thing. You know, like, this is going, so there's, it's like penetration. Or it's either contact on the surface or it's like penetration. This is penetrating the boundary because it goes through, it crosses through the boundary, and it's like penetration. Whereas this is like, it's not contacting, whereas this is contacting. And this is contacting and it's penetrating. So I would say the function penetrates the variable boundary, but it doesn't penetrate the options, the choices, the particular possibilities. Particularity is very much like specificity. I'm not even sure if there's a difference between particularity and specificity. Specific, particular, specificity, particularity, they're like the same thing. Part, that makes me really want to just go crazy. Anyway, Q, power button. Power button is, what is the power button? No, it's like this. That's the power button, or maybe it crosses it. I'm not sure. Maybe this is just like a C, and then there's G, and there's C. What else is there? There's U. All sorts of weird shapes. And obviously O. Oh, whoa, 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 whoa. Oh, whoa, whoa, whoa. Okay, this is a function. This is not. Or wait. I would put it outside maybe? I don't know. But this is a NOT gate because it flips them. Because this fundamentally is symmetric. The two variables inside of this NOT function are the same. Maybe it would be better, like to represent it like this. This is starting to get into something else, but it's very helpful. So you could have this, you could have this, you could have this, and you could have this. But I don't want to do it like that because I want it to be dotted. Fuck. isn't it great how everything is the same? Everything is self-similar, and everyone is just alone without anything at all? No, just kidding. We're real different. No, I don't have nothing. That's not true. I'm not talking about myself anyway. Nobody has nothing. Unless they're dead. Okay. So let's say like this is 0, and this is 1. Or no, I'll do A and B. A and B is good. So this is A to A. It could go right or left. It doesn't really matter. This is B to A, right? This is A to B, and this is B to B. All right, I can't fit it in, but you know what that is. So these show you all of the possible lines, and then what can you do with these possible arrows? Well, a lot. You can do a lot. How would you? Fuck. I should have taken a picture and shown you the actual like page. I don't know if you can see it. If the camera is good enough, then you should be able to read it all. Let's like I'll maximize my my camera for a second just to show you. Oh my god, I need to shave this beard at some point. I want to shave this beard at some point. Okay, now you can kind of see. Can you see? I'm not sure. But you can kind of see this is similar to the shape here. It's an arrow going from 2 inputs or 2 starts to 1 output or end. So many to 1. This is a 1 to many because it goes into here. And then here what I did is I said 0-1, and that was meant to represent a number from 0 to 1 as a probability. So it's like 0% to 100%. And what it would have to do is be probabilities. You've seen that enough. I'll just explain it to you. What you would be doing is you would have a probability, so maybe like 50% or 1/2, and then this is 1/2, and then this would be because the arrow is going this way, it has to add up. Actually, let's do that. Let's make it uneven. 1/3. This can also be 1/3, or this could be like 1/4, and this would be 3/4. So you can even tell, and this would be 1/4. So these probabilities go together. These all have sorry. Fuck, what did I just do? 2/3, I almost forgot. These probabilities go together because they have the same input. So the rows go together because they're the inputs. And if you want to have a definite output for every input, which is what a function is not this. Fuck. Input. Output. A function is supposed to, maybe operation could be more broad than this. A function is supposed to only output one thing. So you find where you are horizontally on the input possibilities, like for example, A or B or 0 or 1, 0, 1, 2. This is your number line. You're one of these places. And so you use the function or the graph, the visualization of the function to find where it goes. But it could also, this is 1 to many. One input goes to multiple outputs because there's 2 functions here. So you could say there's 2 functions in one operation, and that's kind of like this. But that's not quite true. But it is true. But then it's like this to this or something. Is the data type the shape or something? I don't know. The data type is defined by one of these things. That's the pain in the ass that I told you about of everything. Everything is a pain in the ass, and that's why you have to use something like this. That's why you have to use something like this. This is like a fundamental bit. That's just a bit. That's what a bit is. This is a bit. That's how I represent a bit anyway. You can represent it differently. I don't care. Represent. Reptile. No, or not. Okay. Cross the boundary of nothing by death. I'm just talking now. I'm sorry. Okay. These have to add up to 1. 2/3 plus 1/3 is 1. So the reason for that is because it's a probability, and you're basically saying if you have this A, if this is true, then you roll a 6-sided die, or 6-sided dice. Do I have one? I need to grab one. I probably have one somewhere. But you could roll a 6-sided die, because it has 6, and you could divide that by 2. You could say like 1 and 2 are 1, and 2 and 3 are 2, and 3 and 4. Sorry, just like divide the number by 2 and then like round it down. That's like a use for modulus. Where did I talk about modulus? A good use for modulus is rounding. So you want to get rid of the remainder of division. Modulus, remainder of division. That's what modulus does. Anyways, these have to add up to 1 and this has to add up to 1, because 1 out of 1 is like 100% probability. That's the guaranteed probability. So what you're doing by making this probability table is saying if I have an input, I can probabilistically determine the outputs with the fraction of 1, or percentage. It's a fraction of 1, really. It's it's something less than 1. It's something between 0. Prob is less than 1. Actually, it could be equal as well. Let me do this. This is usually how they do it, but there's no it's in Unicode, but I don't want to look it up because it'll take too long. But you can underline it, and now it says less than or equal to. So the probability, that's what prob means here. What I want it to mean is it's 0 or 1 or something in between 1. It's greater than or equal to 0, and it's less than or equal to 1. So this is the max, and this is the minimum. And it's inclusive. That's what the line underneath means, is that it can also be equal to the 0 or 1. So you could say there's like an extra thing over here. Fuck. And this is a 0. And it never happens, because that's just not what this table is doing, because I made the table that way. You can make a different table where fuck is guaranteed, but that's probably not a good idea. That's definitely not a good idea. Okay. This function thing is kind of weird. I agree. One to many is a little bit strange. You have to remember the difference between these solid lines and these dashed or gapped lines. I might try to make every single possibility and get rid of all the words, just so you can see every single possible configuration of the symbols. Because what I would think is this is a gap, like these are gapped lines, right? So this is like a 1/2. This is a state transition thing, and this is what is A to A? A to A. Let me get rid of this solid thing so that it's not selected. I think of the solid boundary as a selection now. I'm not sure if that's the only or best way to represent it, because it's not what it is. Representation is a contradiction because it's not what it is. $1 is not like a thing that it's exchanged for. It's $1, and it represents exchange value, I guess. It represents the ability to tell somebody that something that they say is worth $1 can be exchanged for it, but that's if they agree that the exchange values are equal. But yeah, you could do 1/3. I'm lining these up so they correspond. 2-3. They're aligned now. So there's a 2/3 chance. If you have an A, there's a 1/3 chance for it to go back to A. And when I say go back to, I just mean it outputs A. But you could use that output as like a transition thing. So it goes from A to B, and then maybe it goes back to B. or it goes back to where it was, you know? Like it can go back and forth. That's what these arrows are, is their transition possibilities, is you can transition between these. And this is commonly used in state machines, is you'll have it, this is really important. This is a truth table, that's just something. This is like types of functions, because the function, this is a non-function. No, these are types of functions because every input has an output guaranteed. This probabilistic stuff, that's not a function. Probability functions are not functions. So maybe that's why they're like quantum operations when they do quantum mechanics. Fuck, I forgot. This is also a nice one. I really like this. This is a really helpful thing for understanding things. Notice how it's a table. Notice how it combines these comparison things, which does actually, if you do this in C#, this does literally work. This is how you would code that. The dots are accessing subset members of the object, so it's getting data outside of it. Okay, I'm gonna stop wasting your time. What am I doing? I am wasting your time by doing nothing, aren't I? Oh, this one's cool. I love this one. Okay. What was the diagram I was looking for? I'll know it when I see it. 1 second. It's in my diagrams. I just know it. These are all of the binary functions. It's on the Wikipedia page for functions or truth tables, I think. Here's some cool composition things. This is something to do with tensors being covariant or contravariant. What was I looking for? This is a Petri net, which is pretty cool. Oh yeah, I was looking for Turing machines. I thought of that when I saw this. And then I said it. This is something to do with shapes that somebody made a paper about, and they wrote a lot of words, but I didn't read the words. Okay. What was I was looking for Turing machine. This is also pretty nice. This is a multiplexer. Where is a Turing machine? I swear I have a Turing machine diagram. Here it is. This is the Turing machine. It's a universal Turing machine. So each of these arrows is a transition arrow. And then the transitions, every time you transition, not only is it changing the state, so the state was A, so like the presence, the particularity of it, say there's a presence in the outline, and then like let's say that this is like the state, and this is the variable. So all the variable is all this other crap that I just drew. The state is this outline. So this is how it is now. Let's say I roll a die, and I get, let's say that 1 or 2 is going to be this 1/3, and then the rest of them are going to be the 2/3. So let's say I get a 5, it's going to go over here. The state here, if I roll the die, it's going to go over here, and it's going to become B. So now it's going to be over here. So it's like the outline converted to a dot that moved through the arrow and went over here. Maybe the arrow is like solid, I don't know. Maybe it would only be solid if it was like this, where it's guaranteed, versus over here, it's probabilistic. And here it's guaranteed, it's just like visualized differently. This doesn't even correspond to that. Does it? No, it doesn't. This is just 2 separate types of like this allows you to have 2 separate types of variables as inputs for your function. So this is kind of like maximally, this lets you show all possible combinations of 2 types of variables. The variable is the, yeah, that's kind of interesting. The variable is not the type, but the type requires information to define it. I don't know. At some point I'll explain computer pointers to you too. They're basically just addresses. If you have an address stored in memory, the computer hardware knows how to use that address as a pointer. That's what C, the programming language C does, is it uses an address like 0xA, whatever the fuck, a really long address, but it's like, it's an address. It's a location in the computer memory, which could be like a big grid, or it's just like a really, really long line, and then it's like 0, 0, 0, 1, 1, 0, 1, 1. But then they subdivide it to make even more memory space, and it goes up to like a billion or whatever the fuck, however many bytes, however many bits there are in a gigabyte. How many bits are there? Gigabyte. There's a whatever. Doesn't matter. Okay. State. The state is A, and then because it's a probability, it would like move along here, and then it would become B every time you roll the die, which could be pseudo-random if you have some kind of weird thing like one of those twister functions that's just really chaotic. It's like chaos is sensitivity to initial conditions. So say, I don't know if I have a good chaos theory. Do I have a chaos thing? This is something. Chaos goes out from where it is. Chaos is like entropy. Things go out and they change, they diverge, and if they started a little different, then, but chaos also includes attractors, which is the convergence. I don't know if I have like a specifically like, this is cool, this is cool, this is cool, god damn it. I don't know if I have a specific chaos theory image, but it's like basically sensitivity to initial conditions. So the final state is very sensitive to where it starts, which is true for anything real. Like it's the butterfly effect. It's effects that become causes of new effects, and those effects become causes of new effects, and so on in every ever continuing chains of arrows of cause and effect, the start and the end of the arrow. It just keeps going as long as things exist, which they will continue to exist because there's some kind of conservation of energy. Maybe not including the expansion of space-time. But chaos is basically the sensitivity to initial conditions. So if you have a Turing machine, this is not very complicated, but if you had a lot of states and a lot of arrows, and the arrows were kind of just going in whatever directions, you don't even know, it just like is many different directions, then it would probably be sensitive to initial conditions, and it also depends on what the arrows are doing, of course, right? If they're probability arrows, then it's different from if they're definite arrows, because here it's like, you know what it's doing. Here you don't know what it's doing because you have to roll the die first. You have to say, oh, it was within the 1/3 probability, it was within the 2/3 probability, it was 1 or 2, or it was 3, 4, 5, 6 on the die. And that's how probability could work, to have a changing state machine. So you could do that yourself with a die and even your brain or computer memory, and you could just run that. That's how a Turing machine works. Is every time it changes state, it also does something with the it affects the tape. So it'll move where you are on the tape. Where was that Turing machine diagram? It'll move where you are on the tape. Or this is the infinite tape. It doesn't have to be infinite. Nothing is infinite except for nothingness. I'm pretty sure. But it'll either move the tape. Sorry about that. It'll probably move the tape relative to the machine. So it could be moving the machine instead. You could be moving, for example, and that's like the instruction pointer, for example. Well, that's not really. It's a pointer. It's not the instruction pointer. The instructions are like in here basically, because that tells it how it's moving, how it's changing. That's the program, is inside the state machine. You can write a program and convert it into a state machine. That's what all these functions are doing. Is they're basically, a program is a bunch of functions that occur in sequence, and you could have a deterministic program that's made of a bunch of stuff like this, where it's solid lines, is how I'm representing it, versus gapped lines, it might be probabilities, and then you have to describe the probability, unless it's like, if you don't put a probability, maybe it's, you know, you just say like, oh, well, there's no probability, but it is a probability. It's just, it's even, you know? So this would be 1/2, and this would be 1/2, but you don't have to say it because it's inherent in the system. It's inherent in the possible things that it can change into. It's inherent in the table that you made, because you just go like this, and you're like, because the arrow goes here from the left to the top. And this works self-referentially, but it could also work if this was 0 or 1. And then 0 or 1. If you do this, then it's no longer this. I'm just going to erase this. It's not that big of a deal. If it's 0 or 1, then you've got this other thing where it's A, B, A, that's a weird A, sorry. Sorry, that's not supposed to be A. So this is a 0 or 1. So this would be like, the probabilities that B becomes or is input to the function that produces separately the 1 or 0, or A becomes a 1 or a 0. So you see, it doesn't have to be the same type on here and here, but you would have to say like 0, 1, like you could put another header, and it's an identical header on the bottom and an identical header on the left, and that would be consistent. If you do different headers on the left and right, or different headers on the bottom and top, then you're going to be screwed, because it's not going to line up. It's not going to be the same, and it's going to be confusing. It's going to be arbitrary. It's not going to be defined enough to know what the output is or what the input is, because there's two possibilities. If they're the same on both sides, then it's fine, because it's unambiguous, because it's obvious that A is becoming 0 and 1 is becoming, or B, yeah, that A or B is becoming 0 or 1. You could even say that the variable is A or B, or this variable is 0 or 1. But or is like, does it evaluate the true, or is it like a thing? It's its own thing. It's not an or, but it's kind of like an or. That's a weird thing. And an or, all those truth tables, all these things, they're similar to like everyday speech. We use them all the time, you know? If and only if, true if, logical biconditional. You don't have to write them or draw them the same way at all. You just have to line them up the same way. Like I said, like with this, like these are both bits. Like they do exactly the same thing. It's just when you go to render them on your computer, or you go to write them, you're drawing a different thing. It's a different, unique thing, a different instance, but it's positioned in such a way with these tables that you can unarbitrarily, you can consistently and perfectly determine the output from the input. Or in this case, it's probabilities, because you're putting a probability here instead of a 1 or a 0. You put a 1 here and a 0 here, 0, 1. Then you've recreated the solid line. A goes to 0, okay. B goes to 1, okay. Now it's solid. Now the probabilities are zeros. You can get rid of those arrows. Yeah. So it has to be like a probability for this table, unless you're like trying to waste space. If you're, well, it's not a waste of space though. The real difference between these three different, this and this and this, is these arrows here. You can mix and match everything else. This is like a function variable, I guess. This is a not variable. In this case, F1 is not. This is not. Identity. And this is an identity function. because it outputs whatever is the input. It is the input. The output is equal to that input. Maybe it copies it. It could, an identity function. This is another weird thing, is when you talk about functions, right? We're talking about functions and logic and computation. Logic and computation are kind of equivalent. Whenever you do logic, you can convert that to computation. Either it's deterministically computable or it's probabilistically computable. Whatever kind of logic you have, it's computable because you're using these possibility spaces. Whether you draw them like I do or not, whether you have some reason to draw it like I do or not. You probably do have a reason because I found this, and this is very, very, very big. It applies very bigly. So logic and computation take time. Functions can only be done with time, but functions apply to basically everything. Like, functions are a way for you to correspond any two variables, right? Like, it can be every line is like a function, right? You could just draw a line. I'm just doing it here because it's I'll be right back. I have to pee. Hello, I'm back. Okay, so like I was saying, you can have a line. You could have a line, ha ha ha. I don't know. You could have a line, or whatever the fuck that is. You could let's put 0 on 1. You could just have a line, and then how does the time work? It's not a function because there's no direction to it. Which one is input and which one's output, right? So this is more like an equivalence relation, or just some kind of relation between the different subsets. It's a bijection between the members of the set, is how you would say it in like mathematical set theory. I should say, if you're interested in all this fundamental math stuff, set theory is extremely important, and graphs are extremely important. And I'll talk about graphs in a second. But this is an important distinction, is that this is more like a graph with gapped outlines and stuff inside of it and nesting than a function, because it doesn't have the direction. A function has an input and output, but the funny thing is, you can always just draw the arrow later, right? And a lot of things are like that, where fundamentally, like A is A and B is B, right? Let's say this is I drew this, and let's say they drew, someone else drew this. I'm lying to you, but let's just say that was true. Let's say someone else drew this. They're different, but they're corresponding. And this illustrates the correspondence with the lines. And that's really important for visualizing it. But the interesting thing is that you can have like a shape, and the shape doesn't have direction to it. Like, it could be like that. And it would just be like, you could even have like this, you could have a relation where A goes to multiple, and it's this A instead of this A. It's like, it's whatever the fuck, this is L and this is R. Like, my right is not your right, so nobody knows what the fuck they're talking about when they talk about rights or lefts. But it does have a meaning though, so, other than just space, even though it's a confusing meaning. But you could have it like this, where despite, sorry, I'm looking for something. What am I looking for? Despite it only having, despite it being angular, despite it having, let me find that. There is some description with the truth tables maybe is enough. I don't know. So if you want to understand, I don't know what I'm going to draw with this. I need like another screen. But this is a problem because there's multiple points where this x part crosses, right? So if you have an x, let's say this is 1, what's the y? What's the input? If the input is 1, what's the output? X and y is just what they usually say, but whatever. If the input is 1, what's the output? Well, maybe it's both. And that's like a non-function. So they call it a non-function. So if you have like this, where A, sorry, where was it? Where A, let's get rid of this because it doesn't actually matter anymore. I drew this. But if we draw the arrows, A points to multiple other things, right? Sorry, I keep looking at myself over here because it's on my other screen. The camera is on my other screen, but it's okay. Ice cream's so good. But a function, oh man, that's cold. Tasty though. So a function only has one output. So this is not a function. This is an operation, you could say. And if it has multiple outputs, how does it combine them, right? So if it has multiple outputs, what order are the outputs in? It doesn't make sense. Unless you have something like a probability. I think all of these are functions though. This doesn't have to be a function though. This is kind of like a compressed way if you have two different data types as inputs. This is, so, shit. I showed you this and the one for binary function, or binary variables as well, because a function is defined on the variables. Yeah, so you'll notice many to one and one to many, those are extremely important. That's why I did this. Because many to one and one to many are like, they're used in databases, they're used in functions here, they're used everywhere, because that's just how angles are. So this is like how functions work, but the function, you'll notice, none of these have multiple lines going from the same x, because the x is the input. The x is the input, and the y is the output, and functions always have only one output for every input. So functions, each input goes to multiple, or sorry, each input goes to one output. So it's well, it's not that it's deterministic. It's that when it produces the output, it's only one output. It's not two outputs. Like if I asked you for a NOT gate and an identity, like if I asked you for both of these, this is like it's two functions, right? It's two functions. So when I say this, there's two outputs for one input. It's like two functions, but it's not. It's a shape. See, like if you get rid of these arrows, it's just a shape, really. Like the arrow could go the opposite direction instead, right? You could say these are like two arrows, whatever the fuck you're gonna do to illustrate it. Because it's like weird, because it's like two lines coming towards it. But then it's like it went the opposite direction now, but now it's a function. So it's kind of weird. And that's related to this. Let's do this. This is fun. Oh wait, So now it's still not a function because it's fucked. But let's do this. It's the thing you have to think about it is the vertical and horizontal lines overlapping, right? Because these overlap. There's nothing overlapping here, but here it overlaps, here it overlaps, here it overlaps. So if you swap which one's input and which one's output, you can make it a function when it's not, but you can't always do that. Like I rotated it and this still overlaps with this still overlaps with this. So this curve just cannot be a function. So if you wanted to describe this curve with functions, what you would have to do is have a third variable, and this is called parametric. So x, y, these are variables in parentheses with a comma because you're like representing it as a point, a pair of numbers that tells you where it is on the xy plane. It's equal to, or it's set equal to. It's either equal to or it's set equal to by the function in the computer. So the equal is like equal. The equal sign means different things in different contexts. So it could mean in code if you're writing code and the computer is processing it as code, or if you're processing it as code, you're just like, you know how it works and you're just doing it in your head, then you can do that. But generally it still has a function that's happening, otherwise it's just copying it. So it would be a function of time or some other parametric variable like z or p or whatever input. T is a good one because it helps you understand paths, you know? If you've got time, I'm gonna change this so it's only one directional because you can't go backwards in time, but you can, time does go like, I was thinking of time as change, and that's why I was saying it can go in both directions, because it's like, you could have multiple things that are changing at once, right? You could have, you know, this, my left hand is changing different from my right hand, and it's different, right? Or it separates, right? Time can be a separation happening. My hands are separating. I have to visualize, I'm like, I don't know why I'm looking at myself while I'm doing that. Okay, we're almost done with the good stuff. Discrete graphs are pretty simple. We're almost done. What is this? How would you visualize this? This is like, you don't even know the output type is the thing. The type is defined by this space, right? And then the arrows, this is a type. This is a trit and a number. So it's a number that can only be 0, 1, or 2, right? It can only be 0, 1, or 2. And this is a type, and this is a type. I don't know what the lines are gonna do, if it even means anything. You could use it as like an ordering if you want it to be like automatically correspondent to numbers, but then it's, where do you start? Maybe you would do like this, or like this, you know? And this would be the start. But then why don't you go backwards around it, you know? Fuck if I know what the point of that is. Maybe you need to draw an arrow like that. I don't know. I haven't gotten to that yet. I'm just excited and I'm trying to explain this to you. And I think nothing I've said so far is inaccurate. I just might have been a little bit slow and confusing with it. But I've explained a lot of stuff. So hopefully it hasn't all gone over your head. Hopefully it's helped you understand these things. This variable and function thing is really important. This is a variable. The function has the arrows. So these are all functions. These tables are ways to fully define the functions, but you can also fully define them with like a graph like this. So it shows this. You don't have to draw these arrows here, right? These arrows are unnecessary. They're unrequired because you already know the row is in common. The row has the same vertical position. That's how a table is really useful, because it keeps the vertical position the same, or it keeps the horizontal position the same, so you know that it lines up. And that's why I'm using this for truth tables. And that's why truth tables are used for truth tables. Why tables are used for truth tables is because they work that way. That's not what I mean. Where is the truth table? Maybe they don't have it here. I don't have it here. I mean, I'm sure there's truth tables online somewhere. Whatever. Truth table is literally this. This is a truth table. Here's the names if you didn't read it earlier. Let me find that page again. Oh. Where did it go? Oh, here it is. So this is a truth table. Let me put the labels so you don't get confused. Truth table. This is actually a Cayley table, and that's how group theory is defined. Well, maybe it's not all defined that way. I'm not sure. But and then this is I don't know what to call this. Probability. And this one's kind of interesting because it can have multiple outputs that are possible from one input. Whereas this, for example, you have to put, this is the kind of funny thing is like, this is a number that you would put here. So like 50%, and then this is 50%. And this is like 1/3. And this is 2/3, right? Because they have to add up with each row, because that's the input. Because you have to know like how you're dividing the chance. If you roll a die and it's divided by 6, then how are you dividing that? Excuse me. Ice cream. But this is used all the fucking time. Truth tables are like, you use that everywhere, all the time. But you use it especially when you're learning fundamentals of computer science. There's all other kinds of tables too. Really, you can use a table for so many things. This isn't the only ways you can use tables. But these arrows kind of help you understand like what they're doing. And then you can see like, this is going here and then there, or there, and then there. Here, maybe this will make it more clear. Fuck, what am I doing? So this would be like, it always goes up here. It always goes up here. This always goes up here. This always goes up here. But this is like a dashed line. This is a possible line. It's getting hard to even tell what's going on because there's so much shit. But these are just dashed lines because it's only possible that it goes to one of these and then does that. Or maybe it like, you know, you have to actually check it with the computer. So this is kind of like, you have to have the random number generator and then you have to compare it. So then you're saying like, this is 100%, this is 0%, and then you're dividing up whatever the fuck the thing is, the event probability up into pieces. So you have to like line up the proportions. It has to be 50% in both places, the table here and the random chance roll that you're doing, right? Anyways, I'll probably make a more complete thing about all this. If you read the thing, or if you looked at the book, then maybe it'll make more sense. I'll publish it on my website soon. It's not complete. It's like a little more than halfway full, but I'll publish it anyway, I guess, at some point soon. Cayley tables are used for group theory though. I don't know how to visualize this. I don't know if this is accurate either. Is this accurate? I think it is. It's probabilities, right? So this though would be like A, B, 0, 1, and then this is like, I don't know what's going on here. So this is like every possible combination of the inputs, right? There's 4, and then maybe these like go to the same output or something. Maybe they output the same thing, or maybe they output different things. I hope you can tell by what I'm doing and what I'm saying what's happening. These are possibilities, because these are the inputs, right? And then this is the output. So this is like arrow. But it's a combination of the 2 inputs that have different types. So that's why this is kind of a unique and special one. Usually they're the same, actually. So it's kind of like the table is defined by everything in these locations. You have to know the direction that the arrow is going. If it just goes right or down, then it's just a truth table. If it goes diagonal from one axis to another, then it's a probability table, because it's from one, what do you call this? This is a header. Each of these is the variables are being used as headers for the function table. That's what how I would describe this. This is a variable, this is a variable, this is a variable, this is a variable. This is the header of the table. The variable is the header of the table. This variable is over here as a copy of this variable, or close enough of a copy, is over here as the header. That's how it works. You have headers and cells, and then you have like the corner piece or whatever, which is like the header of the headers. And it's only 2-dimensional because that's all the space I have. I don't have 3-dimensional drawings for you. I don't know how to do that. I'm not good at that. That's bad. That's hard. That's difficult. That's a pain in the ass. Ice cream's so good. But you couldn't view 2D the way you do without 3D. Right? I think this explains it pretty well. That's probably everything for that. All right, now I'll explain graph theory really quickly, because it's like kind of simple. Because really, it's like it's just a thing. All right, so here's what a graph is. A graph is a bunch of nodes, node, and a bunch of lines, and they're connected to each other. So they're like, you know, like this. And the lines go all over. They just go places. Where they go in between might not be important generally when they talk about a graph. This is you can call it a nodal graph. Versus this is what do you call that? 2D. What do you call that? Curve graph? Maybe you'd call it that. I don't know. But that's like what they use when they're trying to x squared equals. If they say like y equals x squared, it's a curve graph. You're graphing the curve of x squared using the 2 different variables, x and y. Remember, it's a variable. And so there's different kinds of graphs. And maybe they'll call other things graphs too that I'm not familiar with, or don't remember or something, but it's close enough. Oh, one thing I was gonna do, I just drew this recently. It's kind of cool. It's like, It shows how a function changes through time. Fuck, that's like something else. But you could say like a change in time. Like there's a thing here, and then the next time tick, it's here, and the next time tick it's over here. Maybe it's not in the intersection. That's kind of annoying to draw. The cross, it's an intersection. It's not a right angle, but it is a cross, I guess. Cross intersection. I think a cross is just like an intersection of lines. Pretty sure. But you could also have intersections like this, and you can have intersections of spheres or three-dimensional objects. You have all sorts of shit. And that's not a cross. So, and two spheres or two three-dimensional boundaries intersecting is not a Venn diagram. So it's like a cross is two lines, two one-dimensional things intersecting. A Venn diagram is two two-dimensional things intersecting. And I don't know what 3D or 4D would be called. But it's an intersection. Intersection is like more generic than cross, I think. Because cross is like, you know, lines. Right? Like a line. Like a little dagger. Pointed up. Sword in the stone. And then you just die. So this is a nodal graph. And the nodal graph can also have directions to it. It can move in different directions. It could have directions to it. And that can be very related to where was it? Did I draw one? It's very related to the state machine thing with Turing machines. Let me find that again. Because it's one set of nodes, right? Rather than, so it's one variable. The variable is the set of nodes, right? The state is the particular one that it's at, the particular node that it's at, that it's located in, and that is the current state. And then the transition, I guess here it's at an end, it's at a dead point. It can't go anywhere, or it's at a, what do you call it? A halting point, or a accepting state, because that means it won't change anymore, but no matter what the input is. But usually these transition things, they'll have, if it's a state diagram, it'll be like, it'll have a function there. It'll say like if tape says 1, move tape left 1. And then it'll be like over here if tape says 0. And it'll do nothing except change the state. So you can put a lot of things on these arrows as like extras that's occurring if you have a state transition diagram. You could tell it to move the tape with that arrow, but then it's like the arrow is actually kind of pointing all the way over here too, and that's kind of like why it's a little not exactly completely describing the directions involved in this, because every arrow is pointing to the tape. Every arrow, or is possibly pointing to the tape. Every arrow has something to do with the tape, unless it's just like a Turing machine that doesn't interact with the tape. If it interacts with the tape, then it'll say something like this. It'll move the tape, or it'll be like, tape says 0, flip 8-bit, which is a NOT gate, you could say. Or you could have like a self thing, and you could say, if tape says 1, set tape to 0. So you could have that. And you could do all sorts of crazy shit like this. And then you can make tables out of the states, and you can make tables out of the variables. You can make all sorts of tables. There's different names that people have that, or had, that that are being used to describe different tables. But I would say like it's basically just it's a variable. The main variable is which node you're in. There's 5 nodes in this graph. That's what the graph is, or the nodal graph. It's a bunch of nodes and lines or arrows. If it has arrows, that means it's directed, and it can also it could also go both ways. It can go both ways, but I'm not sure what the difference between both ways and like a street is. That's a little odd. That's different than this, This is like a trade where the 2 arrows aren't necessarily or absolutely related, whereas this is like an interaction where everything about the interchange is related. Whereas this, it's like, well, what's the relationship between these 2 arrows? They're happening at the same time, I guess, or they're happening between the same 2 things. That was obvious already, because well, I guess it's not obvious, because you could put this here. They're happening between the same 2 things now, or maybe they're not. I don't know. It's kind of weird. But that could be a factor where each arrow maybe could only go one direction. I have a diagram for this myself. It's kind of messy though. Unrelated diagram that I want you to look at. I'm just kidding, it's not unrelated. But it's unrelated to what I'm saying right now. So, this is something. Is that good? And this is something. Where was the better one? This one. I kind of like this one. These 3 rows. These 3 rows are directional, but they can have one directional things. This is bidirectional, so it's symmetrical, right? Equal information, it requires the arrows to have no data content, I guess. So if you're doing something like this, where there's no content in the arrow, there's nothing inside of the arrow, there's no internality to the arrow. Even the if statement would be an internality, even the probability would be an internality to the arrow. Then this conversion thing wouldn't work, so it's kind of like something else. But the idea is unidirectional, multiple directional, or mixed directional. This is kind of like a pain in the ass. I don't know how to describe the difference between these, but yeah, it's either a one-way arrow or a two-way arrow, or there's just 2 arrows that go opposite ways between the same 2 things, which is what's happening here. Okay, that's what a graph is. This is what a discrete graph is. When I say discrete, I mean they're separate. Like each node is separate, and each arrow is separate, and each line is separate. Let's do this, because you can have 2 directional arrows like that as well. I'm not sure what it would do though. The way you use graphs is you look at them and you tell the properties or attributes of them based on those fundamental things that are true about them, like the nodes, the lines, arrow, 2-way arrow. So yeah, in conclusion, the graphs can do crazy shit. This is like how you can make like crazy networks. I mean, obviously, like we're on the internet, you can make a network with all of our connections, depending on what connection means. Maybe like a following relationship is like an arrow, but it's not always. It's like, if you're a follower, they still know that you're a follower, and it's on the list, so it's like it's a filled-in arrow, I guess, rather than a dotted arrow or a gapped arrow. I mean. But it's got something to it. It's not just that. It's a function that runs every single time, and the running of the function is basically running it through the actual physical logical gates. So if we want to talk about computation, I'm going to wrap this up. I'm wrapping it up. Oh my god, it's been such a long video, I'm sorry. I hope this has been helpful. I hope it's been good. I hope my explanation has been helpful rather than a waste of your time when you could have just read or something. Because the reading my book is a little messy and confused, but I can explain to you the things that are arbitrary or not arbitrary, and I basically did that in this video. But the most important thing that's not arbitrary at all is something here. I'm gonna go crazy. Just look at this. Whoa. So yeah, this is the most obvious one that you would want to use more commonly. I mean, this is not this. This is something else. But this is like, this is how truth tables are usually written. If I like, if I pull up a truth table on Wikipedia, ugh, I don't want to show you all my bookmarks. But it's literally just like, it's nothing like a big deal, but you could have true and false, true and false. You know, like this is like A. This is not A. So that's a truth table. Or you could have, you know, like this, where you've got multiple inputs. And if you've got something like this where there's multiple inputs, you can put them together like this. And then you can have the truth table work with that. And that's related to this use of binary numbers, is putting them next to each other and using that left-right order of that we read strings in, right? Because 10 is not 0, 1. Left is where the bigger numbers are, and right is where the smaller numbers are when you read a number, at least with these kind of the standards that I'm used to. I'm not familiar with other standards. I know Arabic is written and written and read right to left. Maybe the numbers work that way too. I don't know. Maybe not. But this, you could have go, you know, anything. True, false, F. You know, so you can have this kind of, you can use the composition of the 2 bits. Do I have that? Or was it here? You can use the composition of 2 bits, right? Composition. Where's the composition image? I love that image. I don't look at it or think about it that often, but it's really cool. There's also this. This is pretty cool. I forget what that's called. This one is something I made, which is pretty cool. Red neurons. I don't know if it's accurate, but it feels accurate. I'm gonna look at it again another time. I keep doing that. I was looking to find threes. So what am I looking for? I was gonna explain, I don't know what I was gonna explain. I'm just gonna look at my diagrams really quick and see if I can find it. What was I looking for? I don't know. I'll explain this though really quick because it's also really important. So you can put all the functions here. So remember what we said, the functions, they're the things that transform one variable into another variable. And then this instruction decoder would be something that you hard code with the functions that you want to be codable. You know, if you want a NOT gate or a NAND gate or a NOR gate, so if you have to pick either NAND or NOR, then you could have either or just a single one of those be hard coded into the instruction decoder, and then it's actually, this is kind of a little weird because you have this instruction load. That's a little difficult, but it would pull the input, and then it would feed it into the ALU function, which you would literally only need either NAND or NOR. You would just have to make composite functions in your code to do more than that. But it would basically be routing everything through the same NOR gate over and over and over. That would be crazy. That would be insane. Writing everything to the same single NOR gate, that would be wild. You would probably want to put more than just a single NAND or a single NOR gate in your ALU functions. This is hardware. This is like how you would graph the hardware in order to produce a computer that's working. If it wasn't obvious, sorry. But the computer has a clock or some kind of way to make it keep ticking after it finishes each instruction. And each instruction is a function. Each instruction is a function that takes input and moves it to output. So you're choosing the input address and an output address, and then the addressing is kind of weird too. You kind of have to I have to figure that out. This isn't entirely good, but it was okay. It was fine. This is kind of interesting. Data types. This is pretty interesting. I kind of like to think of it like this, honestly. But maybe that's a bad. This is like a symbolization, you know, because it's not actually a variable. I mean, these are instantiated variables, right? But it's not. I don't know. I'll re-look at it. But this is you can't oh shit, what did we just do? It's not like you can, it's not like you can fill this in and have it be the same thing, right? You have to leave the true there. So whether it's or you can't do that here, right? You can't the circle keeps things out too. Whoops, if it doesn't have gaps in it. But it keeps things out. Holes in boundary. God damn it. So this is cool. Epic based love. So this is what was I doing? The reason why I did it differently is because if you want something to be inside of it and have it be like this is what it is, then how do you do anything about that afterwards? After you've got it inside of the boundary. There's only two outline types and one internality to every outline, right? That's kind of what these are doing, right? This is the things that, every time you make an outline, you're either adding this or adding this. This is nothing plus a solid outline. So this is this, and then this is an internal outline and then external outline. This every dotted or gapped outline is similar to every other one. You see what I mean? I could draw a line between each one of them. Oh, whoops. So it's like that. So they're all similar. But the fundamental symmetry of these three bound types is that these two are boundaries and this is a bound, but they're all bounds because they have bound. There's a maximum spatial position and minimum spatial position on any coordinate that you give them. They're not everywhere, right? They're not nothing that's everywhere. They're not space-time that's empty, that's nothing. Nothing is not space-time, maybe. I don't know. Maybe nothingness is space-time. But I don't know. So that was why I changed it, because you have to have something inside of it for it to be defined as something, right? If you want to make these, it's weird. So this would be you make an outline, and now you know that you're going to be going here. You know that the function's going to go there. Or you get A, you know that F1 is going to give you B, and you know that F2 is going to give you A, because you know that this is the row that's relevant to your situation, because your variable here, your input variable, is A. It is A. The variable is the specific state of the variable, which is now A. It could be B though. We could change it to B. B. BB. B versus BB. Okay, I think that's pretty clear though. I think we got through all of it. Logic can be kind of crazy because genuinely, you can make so many different tables, you can make so many different variables, and it can get very complicated. Where was that graph of the truth tables for the like 50th time or whatever? Yeah, like look at all these. This is just based on every possible 2-bit input, and it's every possible function on 2 bits. Every possible function on 2 bits. That's what it means by binary function. So 2 bits, 2 input bits. So it's 2 variables that are both bits. So they're both bits. Where is that? Where's the bit? They're both bits. And in this case, they're using true or false, but it could be any kind of bit. Yeah. So you can do that with anything. You can have a trit, you can have however many possibilities you have, and then you can just define the truth tables on them, and then you have infinity. You have everything. You have literally 100% of everything definable by variables and functions. The lines are weird though. The lines and the arrows are weird. Like, you don't really need the lines for the variables. It's just a set of possibilities. The order doesn't actually matter. All that really matters is the function. Like, this, is this 2 the same as your 2? Is this 2 the same as your 2? Or is it different 2? Is this the same 1 as normal? Is this the same 0 as normal? I mean, I drew the number line over here, but I don't know. You have to make the functions for them. You have to make the functions actually do what they do. So you'd have to draw like tables where the inputs and the outputs are the same. So like this would be 0 and 1, 0 and 1, 0 and 1. And it would be like going backwards to the same variable. Or maybe the same type. There's variable, instance and state are kind of like similar. Variable and type are kind of similar as well. But a variable is generally like a type that is going to have an instance. But you don't necessarily know, you don't always know the instance, the particular state that it's in. And yes, this is not how I would describe it now, I guess, because you can draw an arrow thing around it. But that was just this video. I hope helped you understand how you can make variables and make functions and understand how it relates to space-time and make geometry. Geometry has a lot to do with angles. I already explained that. You're just dividing rotations. Numbers. There's numbers, and then shapes are made of angles. So numbers are used for lengths, and then angles can have numbers, which are fractions of the rotation, which lets you make shapes as well. It's still shaped contrast though, like I said on my website. Okay, I think this is everything I wanted to talk about. I can talk about continuous calculus. I'll do that really quick. Calculus is so fucking easy. Watch how easy it's gonna be. I'm gonna explain it in like 2 minutes. 500, 500. Decent size. Okay, here's calculus. You draw a function, so it's only got one output for each input. And then you say, okay, what's the tangent line? What's the rate of change of x with respect to y? So this is x, this is y. So let's say this is delta. This is, there's different ways. This is used for delta x, so this is like delta y. And then this is like, the slope is the ratio of this length it's a length, right? The variables have to be comparable. They have to be numbers so that you can make a ratio. Like if this is 2 and this is 3, then it's 2 divided by 3 equals 0.666666. The devil's number. But that's calculus, literally. It's just slopes. But the cool thing, let's say you know the slope. You know, fuck, do I have a delta symbol? I've got the alchemy delta symbol. Delta x, delta y over delta x equals 5. If you know 5 is the slope, or the rate of change of y with respect to x, then you could say if delta x equals 3, then delta y equals 5 times 3 equals 15. Yeah. But then the interesting thing is the ratio is different from the values here. So what you're really doing, I'm explaining a derivative right now. The derivative and technically you could do delta x over delta y. That would be perfectly valid too. It just depends on how you're trying to do it. Yeah, generally, then you have like df of x or dx equals limit as x goes to 0 of as delta x goes to 0 of f of x. I mean, this is the other thing, is then you start saying like, well, there's like 3 different methods based on this triangle here. So what you're really doing is you're projecting out the slope, or the ratio. That's what a projection is you're projecting out an estimation. Your projection could be a line, which is what we're doing here when we're using slopes, because it's one-dimensional and it's straight and it's flat when you look at it at the right angle. But it can also go the other way. It's just a ratio of f of x minus f of x minus delta x. No. God damn it. Divided by delta x. Sometimes they'll use h for this as like a difference between the two things. But it's basically this vertical difference divided by the horizontal difference. Like I said, it's the ratio. It's delta y over delta x. Obviously, y and x are just names for variables. You can change that. The cool thing, though, is you're using this limit, so you're kind of it's really cool. If you take a calculus class where you learn like dx squared dx equals 2x, like you start to find like these things are just always true, because that's just how squared works. That's just how 2x works. That's just what they do. That's just like mathematically true. So derivatives, even though you're estimating them by doing this limit as the delta, as the difference, so the horizontal difference, you make it smaller and smaller. You could do it centered as well. So there's 3 different, there's f of x plus delta x. I'll just write them out really quick. I remember them, because it's like, it's logic. Oh, whoops. Delta x minus f of x minus, sorry. I'm gonna do all the parentheses so you know too. So there's this, and you're gonna be confused, but it's fine because you can just stare at it a little bit longer, or you can look at the visualization, or you can play with it yourself. Okay. Oh my god, I'm getting confused by the parentheses now. Okay, so this divided by delta x. So you could do that. You could divide it in 2. So now delta x is this, and this is x. So you're finding the slope at a particular point. That's important. You can't just find it everywhere unless it's the same everywhere, like a line is the same everywhere. And that's why you use the line to understand it, because it's a ratio of vertical change to horizontal change, or whatever dimensions the line is going in. But you can also do f of x. Let's do the parentheses. F of x, x plus delta x minus f of x. As long as the difference between the things being subtracted in the numerator, as long as it's delta y, it's still an approximation. It's just whether you're including this part or both in your approximation. But you could also do it like this: x minus f of x. Wait, yeah. Minus delta x divided by delta x. And the delta x, so this is another thing. The d, what they use is, the d is like the infinitesimal version of the delta. So a delta x is like 1 or 2 or something. Whereas dx is infinitesimal. As close to 0 as approximable. And like I said, sometimes it doesn't matter that you're approximating it with this limit, but other times you're just getting the data from the real world and you don't know the shape of the graph, and you're just like a stock market or just like physics that you don't have exactly figured out, that's not predicted by your equations that you're already using, and you have to do the limit in order to find the slope, because you don't already know the equation of the graph as it already exists. And the limit will just go as close to 0 as possible as you can with the data that you have. If you have the function, and the function is continuous, if it's continuous and you can get a really tiny change, right? Remember how we can keep dividing continuous? Even a rational number, it doesn't have to be irrational. It doesn't have to be like pi or e, where there's no fraction that you can make for it. It could be a fraction. You can use a limit. You can just keep dividing it by 2 and over and over and over, divide by 2, until you get really close to 0, and then you've got a good approximation of your slope. And you can use any of these. This is, what is this? So this is, wait. That's like from the middle. I think that's how they define them. This is because this is like x, right? And then this is plus. So x is going to be in the center. X is this point. That's how I'm using it. And it could obviously it could go down too. I'm just going to make it go up though. The point is where it is like horizontally, right? So these are the 3 different ways that you can approximate. I forget what they're called. But yeah. Left hand, right hand, or triangle. Like this is the triangle because you'll make this area, whereas this is like a right hand triangle and this is like a left hand triangle, right? Because it's relative to the point. Everything is relative. Relativity. 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 I don't know. So, derivatives are awesome. But the nice thing about derivatives is they're even cooler. You can use them to get an area under the line well, you don't have to use them even to get the area underlined. But you can also do the same thing and get the area under this, and then maybe if it's like above the x-axis, if this is filled in too, you can get the full area by calculating the area of the triangle. So the area of, let's get some more space. All right, we're literally almost done. It hasn't been 2 minutes, but this is almost it. And then I don't have to talk about calculus in the next video, because that's kind of annoying. Integrals are fucking cool. So integration is the inverse, inverse of dy over dx equals y plus c. And the c is a unknown number. Or it's a variable. It could be a vector as well. And when I say vector, I just mean a two-dimensional variable. A two-dimensional number variable, I should say. There's a number for each dimension, the x and the y. But then there's like coordinate systems, and it's like curved and all this other shit. Then you have like longitude and latitude. But whatever it is, it's still a vector because it has 2 dimensions, and each of the dimensions is a number. So a single number is a scalar, vector. A vector is basically just the line. Wait, no. The scalar is the size of the line. It's only one dimensional, it's just a number. Whereas a vector, it has a direction, so it could be negative or positive too. So you could have, like a scalar can't even be negative. A scalar is either 0 or like 1 or 2 or more, or like half. It could be continuous. But a vector can be negative, I think. So the vector has direction too. That's the thing about a vector, is it has direction. So that's how they frame it, I guess, is a vector is a vector. A vector can go negative because it has direction. That's how negativity works with scalars and vectors. I don't think a scalar can be negative, can it? I don't think so. Which is kind of convenient for describing like quantities of substance or charge or something. Like charge is a scalar quantity that's also discrete because it can only be 0, 1, 2 whole numbers. You can't divide it into fractions. Okay. So as you can see, this is supposed to help illustrate that they're inverses. So you can also literally cancel these out. Dx times 1 over dx cancels out, and then you get delta dy equals y plus c. And again, it's an unknown variable. So let's, that's because this is all you have is the slope. You don't know the y-intercept. So let's say this is my slope versus this is my slope. Let's say that they're the same slope. I'm just going to say that even though they're not, because they're not perfectly straight. And they're not angled the same, I bet. So the y-intercept is different, but they still have the same slope. So that's why this plus c is here. But essentially what you're doing is literally just adding up all the area, and when you're like, let's say this x0, x1, and then you're filling in all this, whoops, you're filling in that area. So this is the integral of my function. You don't have to put y, you can just put f. And then you could put x or input or whatever. Y equals f in this scenario, in this case. So the lower bound is x0 and the upper bound is x1. And then you've got f of x. And then you say dx, and the reason you say dx is because that's the variable that you're integrating over. That's the input variable here. If you're trying to make differences that you're adding up, that's what the integral is doing. You're adding up all the pixels under this area, under this curve. I know it's not straight, it's not right angle, but you know what it means. If you're adding up the whole area, how many pixels are filled in under the curve, how many pixels are under the curve to 0. This is 0. This has to be 0. That's how the integral works. Is it goes to 0, right? Because it's a number. It's adding up the numbers. So f of x is a number, whatever it is. Those aren't even equally spaced. It's adding them up. It's adding up the position. It's adding up the height, right? It's adding up the height. So this contributes so many pixels. This contributes so many pixels. This contributes so many pixels. Let's do it a better way. This contributes so many pixels, then this contributes so many pixels, then this contributes so many, this contributes so many, and this contributes so many. And however you're visualizing it, or whatever data you have for it, you can add those up. And you can do a limit in basically the same way. It's, I don't know if like the, you're adding up, I'll try to, I'll make the limit. Equals, so this is lim is usually how they write it. Lim as dx goes to 0. So dx is supposed to go to, that's like what dx means. That like when you see dx, it's really implying this limit. It's implying that dx is going to go to 0 because it's an infinitesimal, like I was saying earlier. That's what dx is. It's an infinitesimal. So it's like 1 over infinity equals d number. For scalar, I guess, something like that. That's like the intuition you can have for it, right? If you divide by infinity, you're really close to 0, but are you? Did you actually divide by infinity, or did you just get really close? Did you divide by a really big number? I don't know. Anyways, this would be of the area within that dx. So what's the area given some delta x? So let's say like, let's do delta, because that's kind of delta x as that goes to 0 of delta x times delta y. I mean, that's literally that, yeah, delta f of x. Or, I mean, this is also delta y, right? They're the same thing. Delta f, because that's what we're using y as, right? Equal. Yeah, that's the limit. That's it. And you can use the same kind of like approximation triangle thing as you'd use for derivatives. So derivatives, integrals. Okay, there's nobody here to go over this all with, and this has probably been multiple hours, several hours, so I apologize for all your time. I hope this has all been really helpful. I think we've gone over that now, continuous calculus. There is also, like I said, vectors are just numbers with direction. So this is like, you know, you can say this length is x and this length is y, and then the vector is this combination x, y, using this coordinate system because you're comparing it to these lengths here, using that coordinate system to compare it. So that's a vector, is it's got direction to it. Or it's negative. It could just be like a negative scalar maybe. Let me look that up. What is a scalar? Can a scalar be negative? I don't want to say that false. Usually a real number, scalar multiplication. Can they be negative? All values contained on the one scalar of progression of numbers from negative to positive infinity, we shall call it therefore the scalar part. Oh, a scalar can be negative. I didn't know that. Apparently. Okay. So these are, yeah, that would make sense though, because a vector is composed of scalars. So a vector is a multi-dimensional scalar. So a scalar is like one-dimensional extent, and then a vector is a multi-dimensional extent. And, oh, fuck. Oh my god. Okay. Is there anything... I'm just gonna blur it out later. All right. So this is all the different types of tensors. And you can see M and N are actually, like, there's scalars and there's vectors here, and there's also a covector, and you'll notice that those are actually basically the same kind of thing. It's just one is a row vector and one is a column vector. So it's like XY versus XY. So it's kind of insane like that. Like, they like to do it that way, but that's what a tensor is. So scalars, vectors, and tensors are also extremely common in geometry and calculus. But the way that these are used, the reason why there's so many different things here, this is just from the Wikipedia article on tensors. The reason there's so many is because there's different ways that you use them, because you can use them like these function tables, I think, or something. Or you use them like for matrix multiplication, basically. It can get really complicated. That's everything I wanted to cover, though. I'm gonna go over these things next, and it's gonna be interesting. This is kind of like our physics, you know? And you can ask, like, why do we have those physics? And I can't tell you exactly, but I'll explain kind of how they work a little bit. And then this is kind of like more fundamental to space-time, I think. That's just like every universe has these things. Even heat, like heat is just motion of particles versus of the composition of particles. So thermodynamics is like a universal thing, as is entropy, which is related to thermodynamics. Cosmology and astrophysics, I guess that's specific to us, but it's relevant to all this shit. I might even put it after all of this, because if you're talking about long-term, but it depends what you mean by cosmology, I guess. But like, I mean, astrophysics, it's like, are you talking about engineering? Are you talking about things that like humans or AIs could be doing? Versus, are you just talking about, you know, stars and planets and moons and asteroids and balls of matter held together by gravity? Okay, that's everything. I hope you liked it. Holoscope. Is there anything here I want to talk about? These are all like types of graphs with certain numbers of nodes that are trees and not webs, so they have no cycles. These are all the things that you can make stuff out of. These are branches, so it's like you could even, I was gonna kind of combine these with the branches, like it's just two things related, but there's an asymmetry in this, and there's like asymmetries here with the way that you're drawing them, and there's just asymmetry everywhere, really. And then there's graphs, which you can kind of understand here. A cycle is just, you can trace a line along the lines that makes it reaches the starting point again. Is there anything else? Compositions, yeah. Ha 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 ha. Funny. Yeah. It's just physics and math. Anyway. Alright. I hope you liked this. I hope it's helpful. Let me know if you'd like me to make videos about any other topics. I'll make a video about this and then another video about this probably separately. Yeah. Okay. Have a good one. Have a great life. Bye. Hey, I'm adding on some extra information to this video. I wanted to explain the structured program theorem because it's really relevant to programming. And I also kind of wanted to talk about distinguishing as it relates to these. Distinguishing is kind of like using conditions or cases, which I'll explain what they are better with this thing, in order to tell differences between things. So you're telling a difference, you're taking an input of differences and you're outputting some distinguishment or distinguishing between the two things that were different. So maybe a cat and a dog, you're distinguishing them by the way that their ears are, the way that their body is shaped somehow, like or like how long their hair is or something tells you their breed, I guess. But you're distinguishing it based off of the inputs. So we're still using these functions. I want you to still understand the truth that computation, all of it, is using these functions between different locations in memory. What you're really doing is still always going to be, like every line of code, each one of these statements, you can see the conditions. So let's talk about that. There's statements and there's conditions. That's not a bad way to say it at all. The statements, you could also say in a different way, you could call them expressions. But let's say a statement is, a statement does something. Sometimes, so calls functions to transform data between memory locations. So I think I have a good, the image that I showed you earlier, even if it's not exactly a way a computer, here's this. These are like very relevant. So I'll kind of explain how a computer works really quick. Just because I was supposed to talk about computation, but I didn't really get to it in as detail as I wanted. And this is my model of a computer. It doesn't have to look like this. It doesn't have to be shaped like that, but it generally has like all of these things. A computer will have all of these things. It'll have an instruction pointer so that you can program it. Otherwise, you can't program it because it has to be able to point to where the program currently is in memory. So the pointer is pointing to like 0, 1, 2, 3, 4, 5. Each one of these rows, you can see there's an arrow, there's a memory location, and there's a function. So it's either calling a function, it's got this f and then the parentheses in it, or it's just moving between memory locations. The instruction pointer is just a special memory location. The red is for memory locations, and these are special. Everything has memory locations. You can think of it that way if you want. But the instruction pointer and these memory locations are the ones that are accessible to the pointer system, or to the machine. Like they're the changeable memory, I should say. All the rest, it's hard coded basically. The instruction decoder will always decode the instructions the same way, and the ALU functions, when they're in hardware, that's the hardware that's going to do those functions. Unless you want to swap it out somehow, but that's a difficult thing. And then there's like the differences between the address and the thing at the address and what kind of address you're using. But what I want to go over, when you think about that, it's calling a function, so it could be like A equals f of b, or you could just like, so a statement, I think what they mean by that is like f of b and then a semicolon, or like just f of b. So f of b, what this is doing is you're not showing where the function is outputting to, and the function might not even output anywhere. It might be doing a bunch of stuff and then the output goes nowhere. But this is what's called a pure function, is because if it's a pure function, it's going to do nothing because it's not going into anything. This equal sign, it's like an arrow equal sign. It goes left. The output goes left. So the output of the function will go into the a variable, and that's what do you say? A set. You're getting the output of the function and you're setting the value of a. Yeah, but this, a pure function is basically you send input and you get output. But if you have a non-pure function, you send input, you might get output, and you might also get side effects. So this f of b, the side effects could be some other thing that f has inside of its code. If you have a more complicated code defined inside of the f function, using whatever programming language you have, because you can define it. And that function could be accessing other memory. It could be doing basically procedures to actually do the setting. It could have a statement like this inside of the function, and that's kind of why it's happening, why it's a little confusing to have side effects. Ultimately, though, when you get down to it, it's still fundamentally doing this every time that it's setting data. So you can think of every single actual change, every single actual operation, every single thing that's happening, a thing that happens, an event, everything in code, all the stuff that actually happens in code is doing this. Maybe the function just says a equals b, like a is set equal to b. Maybe the function is just an identity function, but it's still setting something. This either does nothing or it sets something. Maybe like c is inside, like f of x, and then you say like c equals x times 2. And this is not a pure function because it has side effects. It's using c. It's referencing variables that are not in the input. Therefore, it's not a pure function because it has side effects. Like this is a way to visualize that. C is the side effect. So c is over here. This is A, B, B. And it's possible. You don't know what f is doing. I don't know if that's what f is. But this is a pure function. This is a pure function. This is a non-pure function that does side effects. You could say it has side effects or it does side effects. It's the same thing. When I say it has side effects, it's because what's inside of it and defining it is like the information that you're calling over in these ALU functions, or the memory with the code. If you've got a function defined like I did, because you can define these functions. You can say def f of x and then whatever, put it in curly brackets, and that's the function. You defined it. Whatever the fuck this does, I don't know. Maybe these letters do something. But all of the statements are calling functions, whether they because they're using logic gates, they're all deterministic. They could have multiple outputs if you have like some random number thing, but that would still require collecting the randomness first, and then using that as an input to a deterministic function. So it's a little strange. But this is like really important. This is extremely important. These are ways you can visualize 3 different fundamental things. So this is like, this is sequence, selection, and this is repetition is what they're calling it. So let's get a little bit more space. So sequence, you're just doing these in order. So you're just like, grab my water bottle as the first function. See, like you could write it on a list. Like let's do it right now. Well, it's kind of weird. It's like, what is the output? It's like, I don't know if I can define that, but let's just say drink water and then play with my lighter. So that was in sequence. That was one after the other. You can see that, like, you could imply that there's an arrow here between each one, and it just goes down. That's just the way the code is structured generally. Doesn't have to be though. Does not. So and then there's this. So this is if then else statements generally, and you've got like a start, and then if x is greater than 0, for example, else. And you would, and then you've got like some other stuff going on here, and that could just be more code, you know? It's a path in the code, so you can, I'll show you. If x is greater than 0, then you do some stuff, else, and then you could also have an else if, and you could say x is less than 0, maybe you care about if it's equal to 0, and then you can say else. And that you might not always know when the else is going to get called, when it's going to reach else. If you know what else means, then you know this, how this works, because it can only go down one path. If this is going to say, oh, I'm either going to go here or I'm going to go here, and then this is going to say, oh, I'm going to go here or I'm going to go here. So if the condition is true, it'll go into the curly bracket shape. Or if it's false, it'll go to the next thing in the if-else-if chain. So you can have a bunch of else-ifs. You could say if x equals 1, if x equals 2, if x equals 3, but then it would be else of if it's greater than 0, so that would never get called. Because if this is another thing, yeah. Else if is kind of weird. Else if, that's the case that I was talking about, I guess. So, God, it's a little confusing. Else if x is greater than or less than 0. Else. So you've got 3 possible places that it can go to. And this, it's gonna go, well, it's a little weird. I have it in my book. Let me see if there's like a better way to draw it. Oh, here it is. Yeah, it's okay. I mean, you kind of have to put the condition, like if you're, let's do it this way. So let's say this is the if, and maybe this is like all the specificity of your, excuse me, sorry. This is all the specificity of this selection, of your current context, which is all the current, or really maybe even the current scope. The whole scope is in this. The entire scope is in this, of the current code functioning that is occurring. And when and the scope is basically all of the variables defined within a certain like curly bracket, or like this. Like if I say C, you know, like over here when I was saying C, like C is still in the scope. It's still available to be, like, you can send data to it or you can get data from it. The context, no, I think scope is related to the code actually, but it's like the contexts are in the scope. So I'm not sure exactly. Isn't that funny? But let's say if is here. So you would say if true, it goes this way. You could make it the opposite if you draw it that way. And then it goes over here. So the if is right there, but then what do you do after that, right? So if you've got like an if else if, then when you reach false, what you have to do next is have like another if else. And this is optional. You could just stop right here. These are just like, think of the circles as like different positions in the code. So you've got if x is greater than 0, else if x equals 0. I'm just doing that so you don't say something. You could also just do 1 equals, and then else. So each scope, a scope is contained in the curly brackets, and then the context is like all the variables that go into the scope, I guess. Something like that. So this would be like it goes this way if it's true, and it goes this way if it's false. And then how did I draw it? And then after, oh yeah, that's fair. I could do that. So you could say, you could put the scope right here, and then these each have their own scope. So this is the else case. And then this also has its own, I can't draw curly brackets, but I can enough. And so something in the arrow, there's functions in the arrow. All code is just functions. I promise you that. All of it is just functions. It's complicated functions that are one after another, but it's each one is a function. So you can think of that. It's like there's all the memory. Think of this as like all of this. It's gonna be it's gonna go here, and then it's gonna go here and then here, or it's gonna go like here and then here and then here and then here. And over here it's gonna have changed. Every time it goes through these scopes, more functions get called. More of these things that produce output different than the input. See? All these functions get called between the memory locations, which you can address, or you can use a variable name to address them. Like this, home is like a variable name, for example. But then it's over. And then it kind of collects afterwards back at the end. So, yeah. And you can kind of think of it that way, like this goes here, and this goes here, right? So I don't want to draw arrows over here, but I guess you could. But it goes to the if else, so it has, if this fails, then it goes to this. And then if this fails, it goes to this. And the only way you ever reach the else is if none of the else if conditions were true. So this is kind of like a chain. This is a common thing. It's a chain of if else ifs. You could also do it a different way. Oh, that's weird. You could also have switch and then var. And this kind of does a similar thing, but it doesn't always work the same way. Case 0, and then stuff, case 1, so it's doing stuff, I should say do stuff. The parentheses is how you know that's a function. So it could have like side effects and whatever, you know. It's calling another set of code. It's going into another scope that has all these, that can have whatever functions you define it as. So a switch statement can work like this, and then it can even have a, is it called an else? I think it's called default. And then it's kind of annoying. I don't like how they make you do it though. But it's like, it doesn't work the same because these are expressions that evaluate the true or false. They use, what is it called? The compiler tree. Like the compiler tree is already there and it just does the functions and it produces a true or false value. And if it's true, it goes down a different path than if it's false. So that's just how it is. And you could make your own with ones and zeros because it's a bit, right? What else? Switch statements are kind of annoying. This is like more general, but it's still selection, right? You're still branching, yes or no, true or false. It's the same exact thing. That's the condition, see? The if is the condition. There's also this, which is a while loop. So let me draw a while loop. You can do loops a little bit differently depending on what you're doing. Here, let me show you the image, the part. Fuck. You can kind of see. It's just different shapes. And then the arrows will have the conditions that they require to go down on them, I guess. Maybe they should be gapped. I don't know. Whatever is most clear and unambiguous is what I think. So a while loop would be more like this. You would have while, so while 0. So you've got your stuff, your specificity that goes into the code, all of the memory that is accessible to this code based on the programming language that you're making or using. Which if you're gonna make one, you have to make like a compiler and stuff. So it still has to fundamentally work with instruction sets, which is fundamentally, like I said, doing this setting with a function. You're just taking input, changing it potentially, or leaving it the same, and putting that somewhere. It could be the same place. It could be like a equals a plus 1. God, I hate that. It could be a is being set to a plus 1, right? And that's just an increment. You're just adding 1. That's common for while loops, for example. You want your variable to change if your condition, if you're in the, so let's draw it. So true, false, and you're here. So this is in the while loop. Let's say this is the scope of the while loop. It goes right there. But then ultimately, this is going back here, and eventually it's gonna go somewhere else. Does it go like, what did I do? What did I draw it with? I guess I just put it here. You don't need to add anything else though. This is the end. So this would go if the condition here is false, it'll go out over here. And that's what this is doing, is it's just a loop. If it's true, it goes to the statements inside, it goes to the scope. And then if it's false, it kind of goes around it. And just continues on. You can structure it a little different. If you draw the arrows different, you can have a do while loop, and that will always execute the code at least once, because it does it, and then it comes back to the condition. I'll see if I can draw that really quick. So this is where the scope would be, and then this is where false is. So it's checking the condition at the end instead of the start. So this is while, and this is like do. So this is like a do while loop. Do while, or I think you draw it like you code it like this. So that's kind of how that looks in code. But that's literally how code works. This is extremely powerful. I mean, you can make all sorts of weird data types and structures and object-oriented crap and functional, all sorts of different programming typologies, but fundamentally it's about this control flow. You're controlling the flow of the program by using these conditions that evaluate to true or false. They evaluate to discrete outcomes. It's either true or it's false, right? One or the other. It's either 1 or 2 or true or false. It's a bit. It's separate. That's what the difference is between discrete and continuous. Discrete is separate, and continuous, it's all together. Continuous is just everywhere. Whereas discrete, it's like 1, 2, 3. It's like a hop, you know? They're separate. My hands are separate. They're discretely separate. But maybe they're in continuous space. Maybe they're defined by continuous things. Whereas a computer, you can define everything in discrete terms, and that's like calculable versus real numbers. If you want to know all the details, all the digits, it's like a pain in the ass. Like, what about pi? You don't know all the digits for pi. But I guess I was thinking about the word distinguishing too. I wanted to explain that. When you do these um, control flow statements, you could call them control flow conditions. A condition is really a important way to think of it. When you do these, you're telling something apart. You're saying X is one way or X is another way, and you're using that for very important things because you're doing totally different stuff. There's a scope here and a here and here. This is totally different from this. It's totally different from this. They're totally different. They could have similar stuff. I don't know, but they're different. So when you decide that something is worth distinguishing, then you decide to do you make one of these structures to control the flow of the program. Whether you're a programmer or not, you've been doing this the entire time you've been alive. I guarantee you. You repeat things, you select things, and I think distinguishing is both of these because both of these have conditions to them. And when you tell something apart, when you say it's truly this, it truly meets this condition, or it doesn't meet this condition, does not, it's false, then you're distinguishing something about it. And if you can compare it, if you can have this comparison operation, I didn't talk about this before, greater than, less than, greater than, equal to, less than, equal to, is that it? Maybe like within, I don't know, that's not a thing. Is there anything else on keyboard? No. Well, there's arrays, but that's just like boring. That's just like a set. Should I explain arrays? An array is like that, and then you say z equals. So this is an array, and you say z of 1. So like you tell the computer to print it. So this is how you tell the computer, maybe in some programming like Python, this is how you would tell it to print it out to your command console, which is the output of the program that you can actually visually see, or that you can feed into something else if you have some way of piping it together, which command line does let you do a lot of. But that would print, this would print 0, or sorry, this would print A, because arrays start at 0. So this is 0, this is 1, 2, 3. These are the indices, and this is the array. So then you have array name, and then you can access the members of the array like this. That's a very common thing in programming. I'm not sure how you could do that potentially, but it's just a list, it's just a set. It has an order. Otherwise, you wouldn't be able to know the addresses. This is an important thing. When I talk about addresses, it's not different from indices. It's like fundamentally the same. It's just whether it's like a two-dimensional or like, is it like a, it's not a coordinate. It's not where is it? It's not an XY combination here with the indices. It's just a single scalar discrete number that tells you where it is in the array. So you could have, oh my god, and you can have multi-dimensional arrays. Which is like that. And then there's like stuff in here. And then you need like z of 0, 1. So this would be the 0 here, and then if this was like 0, 1, or a, b inside of there, then this would give you b, because that's the second element. It's 1, so it's the second. I know it's kind of weird because they start at 0. They don't always start at 0, but it's kind of good that they do, because that's how you it's a displacement from the memory location. If every memory location is just a number that they use as an addressing system in the machine, and if you have the exact address, it's unsafe because well, if you can get any address, then you can. It's unsafe because you can access the entire computer. You're like an admin that has unlimited access. You could break everything. You could delete your operating system, and that would be bad. But yeah, arrays are kind of useful for that because it starts at 0 because if it's the array is a pointer to one of the memory locations. That's the point. It's a pointer. And then all you have to do to get the other parts of the array is to know the length of the array and to do a displacement. So if you think about that, like where the length is stored is kind of its other thing because you could have it end with like a special null character. So it's like, but that's like how strings work, is they end with a null termination. So it'll be like A, B, C, and then like \0 is like how that works, which is really fucking weird. So like this is how a string is like structured, is it's these individual characters and you have to like, I didn't do it correctly over here. You're not supposed to do this because it's supposed to have, you're supposed to distinguish the string or the characters from the variables that they might be referencing, because without the apostrophe you might be referencing a variable, right? But if you put them in the apostrophe single quotes, then you know that it's the character, it's the symbol. But yeah, usually strings are just an array that ends at this, and then if you wanna see the whole string, all you have to do is just keep adding 1 to your address until what you find is a null character. And this null character, it's probably like literally just all zeros. Whereas most other things are gonna be like there's a lot of bits in most of these data types, but like some other, like maybe this is like the first actual character, whereas this is a null character, so this is gonna end the string. But that's null terminated strings is a common thing. Or you could just have the length defined somewhere for the array, like maybe it's maybe in memory is just this. Memory is the tape of the Turing machine. So maybe it's like 4, 8, 6, 4. So maybe it works like this, and your array points here with some address like 0x crazy shit. This is your starting address, and then you keep going. Maybe the way you could make an array work is the first one is the length of the array, and then the rest are the contents of the array. But it really depends on the data type that you're using. In C, it's very particular. You have to have the data types all line up very nicely, whereas other languages, it kind of does more work for you in terms of conditioning your data and trying to make it work together, trying to implicitly convert them into one another or explicitly convert them into one another using functions. If you can convert a string into a number or a number into a string, depending on how you line it up, you know? If you have a truth table, it'll work. And usually there's like the default ones, like, you know, 0 to 0 or 1 to 1, 2 to 2, like 2 corresponds to the number 2. So most programming languages will automatically implicitly convert these between one another, or maybe they'll implicitly convert only one way because they don't want to fuck up. But maybe they'll do it both ways. Who knows? You could do that if you wanted, but maybe it's not a good idea. I don't know. Okay, I think I've explained enough code now. Hopefully that wasn't too long of an addition. The video was already really long. But yeah, I hope you enjoyed it. Have a good one. Hey, one last final thing that I just kind of wanted to go over to explain how this actually works. The sequence is pretty obvious. Basically, the clock instruction pointer just keeps ticking through the different lines of code. So if there's a line of code here, then there would be a line of code on line 1, then on line 2, then on line 3. But let's say I've got a Python program that says def my function let's. What am I trying to explain? I'm trying to explain how you're basically using the instruction pointer. That's kind of what I want. That was my goal. That's my goal here, is to explain. You're basically using the instruction pointer every time you want to have a condition. What you're really doing here at this if or this while or the while of a do while, what you're doing at these branches or the if else, really any of these branches where you're evaluating conditions, think about it this way. It's basically it's a function that's outputting to the instruction pointer. So the instruction pointer is what you're using in order to determine where your code is located. So it's loading the instruction, and the instruction goes into the instruction decoder. So this is the instruction, 0x0000, arrow to from f of 0x000100, and parentheses. And so each instruction is really, it's only an instruction technically if the function is in the ALU, it's like hard-coded. Otherwise it's just a line of code. But if it's assembly language, then all of the functions that are being done are gonna have like a definite memory location, and they're gonna have a definite function. So this is really important. This conditional goto, this goto and this conditional goto. You can think of goto. It's kind of unrequired for regular programming, because if you go 0, 1, 2, 3, 4, 5, like the clock will just increment the instruction pointer one after another. Or if you have some kind of thing where you know when the instruction has been completed, then you can have a signal go from the instruction decoder to add one to the instruction pointer, just like automatically, and then that could just keep going until there's like some end of the program, you know, the halting mark that just says like return or whatever, return 0. There's like standards for that. But the conditional goto is really important for these two, because what you're basically doing, if you have like I don't know how to say it. Like let me just draw the function, because that's easier to do actually. So if you had, let's say you've already evaluated. So maybe like there's some stuff on the left that is like already done, and that stuff is cool. So you've already got a true or false evaluated inside of your condition. The condition could be x is greater than 0, but let's say we've already calculated that. That's how it has to do it with the compiler tree. And then once you have true or false, then what the condition is just a straightforward mapping or function to some address. So this is the address A or the address B. So if those are addresses, like this is A, this would be A, and this would be B, right? Or those would be addresses in the computer code. So you could type it as go to A, and that would basically take you to the A part. Or if you were trying to be extremely literal, you could say go to line 3, and that would take you to line 3. And this is really important if you want to make coded functions, if you want to define functions, if you want to have defined functions that can have side effects, then you're not just doing this. If you want to have side effects, you're not just doing this. You're defining the function like def f of x, and then you have a bunch of code. And that's the function, you know? This, and then you could have even more crap. Whatever the fuck you're doing. But the function could be all of these, it could be doing all of these things, it could have these side effects, but only because it's got multiple lines of code that are doing different instructions, it's setting things at different locations. It's not just setting to one location here, it's got multiple lines of code, and each line of code could be doing something like this, probably is doing something like this, otherwise it's meaningless, it's not affecting anything, it's not doing anything actually, it's just a code that does nothing. But this is going to get you, say, an address like home or whatever, and then what you would do is you would have it be set the instruction pointer with that, and that would basically set the instruction pointer so that now you're at line 3, and that's a go-to. So this def stuff, you have to have some stuff behind the scenes to handle that, but essentially what you're doing is when you call a function here, like this is how you call the function, but it's defined somewhere else. So when you call the function, what it's actually doing behind the scenes is it's doing this go-to. It's an unconditional go-to. It's going straight to it. Maybe it does some copy work first. It has to copy things to the register, some faster memory, because it's not all actually in one. It's usually multiple memory banks, because some are faster than others. But this memory stores, whatever. But this, the go-to is setting that instruction pointer so that the next instruction that gets run by the CPU, the instruction decoder, or the GPU, whatever the instruction processor is doing. I guess this whole thing is the processor, really, or all of this is the processor, and the memory is there, and the clock is like part of it. But it's utilizing these two. So calling a function is a go-to. You might copy some stuff to like load in the inputs for the function so that it knows which ones are the inputs, and that's what the registers are. You would load in like a pointer for input A, or the first input, then the second input, then the third input. You would load in pointers for each input, and that would be your loading thing that you do before the function. I know this because I've taken a class on it, and this is how you call functions using assembly code. You have to manually do these operations every time. The function, it doesn't actually exist unless you have physical logic gates that it's going to carry it to. If you want it to go to your own custom function, you have to use the instruction pointer to make it reference the code here, or the code here, or whatever, in your defined function. So this could have def f or whatever inside of it if you're doing something in a certain language, you know. I'm thinking of making the _10 like an assembly language program with, you can only use like certain primitive functions and data types, and it's all instructions, and you can't define any functions. It just uses the basics. And then one wavy O is going to be like, you can define your own function, so it's going to be really complicated and object-oriented probably. But that's kind of what I want to say is like conditional go-to, you're using, you're setting the instruction pointer to go to wherever this code is. See, remember how there's a scope? You're going to that scope. You're going to where it starts. And that's over here. So there's this behind the scenes, what the compiler or interpreter, whatever it is doing is it's doing conditional go-tos. That's what this is. And let me just make that clear. Like it really is like this is where the instruction pointer is now. Like you're setting the instruction pointer. Like this is the expression and this is the instruction pointer. Or it's like I don't know. There's like different words for it, different acronyms, but that's what it's doing. Is it's setting the instruction pointer based on a function of it. So this comparison operation, is a function, and it outputs true or false, and then the true or false is just mapped onto or functionally put onto a particular instruction pointer location. So the instruction pointer is pointing to instructions. That's why it's called an instruction pointer. So it points to a particular instruction, let's say instruction 2. So that would be jumping or a go-to that line of code. And that's the thing about the condition is it's using the function, it's using this expression evaluation. The condition is really something like this. So this is like an f of x. F of x equals x is greater than 0. This is a function. It's just a function that evaluates to true or false. And that's great because we can use it in this condition right here in ifs or whiles, while loops or if statements. And that allows you to dynamically control the flow of the program by setting the instruction pointer. And that's kind of one of the most important things is this conditional go-to. All four of these are essential to operating a computer. All four of these are also essential to operating a computer. Otherwise, you're going to forget what your names are of your variables, you're going to forget what things are, or you're going to forget where they are. I think that's everything, though. I think that's everything I wanted to explain. This is pretty cool. All right, this is a very long video, several hours, but it covers a lot of really helpful stuff. Like I said before, I'm gonna separate it. I think I'm gonna talk about this physics stuff, and then I'm gonna talk about more like emergent. This is like emergence, and this is like physics. I just use emergence as like an easy catch-all word. I can just say everything is emergence. Chemistry is emergent. All of this, physics is emergent, probably, you know? Like, a lot of physics is probably emergent from just, like, logic, and space-time and computation. But a lot of it isn't. It's very particular. That's why there's the fine-tuning problem. I don't know if I'll talk about that. That's kind of a cosmology problem. It's like, why does our universe have the laws of physics that it does? All right. Have a good one.